A magnetar doesn't need to hit Earth to end it. One silent pulse, and the chemistry of life can simply fail. No crater, no fireball, just an invisible shockwave sweeping through space, rewriting matter as it passes. If one ignited within 1,000 light years, would we even notice before everything electronic and everyone alive went dark? Somewhere in the Milky Way, a dead star is holding a charge big enough to bruise a planet from afar. It is small, silent, and unimaginably tense, like a loaded trap hidden inside the dark. We call it a Magnetar, and the name is almost too gentle for what it implies. 20 kilometers across, it carries a magnetic field so extreme that ordinary intuition begins to fail. Around it, space is not empty. It is structured, stressed, and threaded with invisible force. Light itself can be bent into an instrument, and radiation becomes a kind of weather. The central question is not whether magnetars are violent, but what makes them uniquely lethal across distance. How close is too close, when the threat is not impact but physics arriving at the speed of light? To answer that, we have to follow a trail of clues that begins with a stellar death. A massive star collapses, matter is crushed beyond chemistry, and a neutron star is born. Most of these remnants become cosmic lighthouses, but a few are upgraded into something stranger. In those rare cases, magnetic energy dominates everything: spin, heat, and the rules of the surrounding vacuum. We will step into a regime where fields can outmuscle atoms and rewrite how particles move, where the crust of a stellar corpse can fracture, and the fracture can echo into space. These objects do not merely shine, they store stress, and sometimes they discharge it without warning. When that happens, detectors saturate, satellites flinch, and the sky briefly behaves like a weapon. Yet the danger is not a Hollywood blast, it is a sequence of subtle conversions and a long aftermath. A planet can survive the first moment and still lose the conditions that made it habitable. The most unsettling part is how ordinary the night looks while all of this is possible. Because magnetars are rare, and because our maps are incomplete, uncertainty becomes part of the hazard. So this documentary is an investigation into the most extreme magnetism we know and the limits of our safety margin. We will weigh real events against models, follow the evidence through timing glitches and gamma flashes, and ask what the sky has already told us. And as the picture sharpens, the fear changes shape, from helpless dread into a problem we can measure, not to make the universe comforting, but to make it legible, one observation at a time. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. Across 7 chapters, we will trace how magnetars are made, how they break, and how far their reach can truly extend. Then we will turn to the search itself, building better nets before the next signal arrives unannounced. No impact, no fireball, no warning sirens that make sense to a human brain. A hard flash crosses deep space and reaches Earth as pure, indifferent radiation. For a few seconds, the sky looks normal because the threat is mostly invisible. Satellites above the atmosphere register the surge first, numbers spike, counters chatter, and then the data stream saturates. Down on the ground, clouds drift and birds keep flying because nothing seems to have changed. Then the chemistry of the upper atmosphere begins to fail in fast motion. X-rays and gamma rays tear apart nitrogen and oxygen and make reactive fragments. Those fragments cascade into nitrogen oxides that shred ozone faster than it reforms. In simple terms, the air becomes a chemical factory that produces its own poison. The protective layer thins, then collapses across latitudes that never expected it. What was once a thin global film becomes patchy and ragged, like fabric pulled apart under stress. Within days, ultraviolet floods the surface and turns sunlight into a biological weapon. The UV is not new, but the filter is gone, and that difference is everything. Plants bleach, plankton die, food chains buckle, and ecosystems lose their base. In the ocean's sunlit skin, phytoplankton stop dividing, and the carbon cycle stutters. On land, leaves lose pigments, seedlings fail, and shallow water turns strangely clear. Life does not need to see the killer to be changed by it. The horror is not heat or noise. It is inevitability and distance, cause and effect separated by the cold geometry of space. Nothing has to touch Earth. The pulse only has to pass through our air, and the atmosphere does the rest. The kill mechanism is physics working at scale, with no malice and no mercy. If the flash is strong enough, the biosphere becomes the target by accident. That is the premise of this space documentary, and it asks what could do this. It also asks a quieter question. How many times has nature rolled these dice, unseen by anyone alive? The answer is a magnetar, a neutron star built from collapse and extremes. A neutron star is already a stellar core crushed into a city-sized sphere. Its gravity packs more mass than the Sun into a diameter near 20 kilometers. To picture that, imagine a mountain compressed into a teaspoon, until matter itself resists further collapse. Its surface is solid nuclear matter, and its crust is locked under immense strain. Under that crust, neutrons form a dense fluid, and pressure replaces chemistry as the ruling force. A magnetar is a special subset. It is defined by magnetic violence, and by the way magnetism becomes a stored explosive. Magnetars carry magnetic fields around 1014 to 1015 Gauss. Earth's field is about half a Gauss, strong enough to guide compasses. A hospital MRI magnet reaches about 10 to 4 Gauss and feels like advanced technology. A magnetar exceeds that by 10 to 11 orders of magnitude beyond intuition. At those strengths, the field is not a background detail. It is the engine, an energy reservoir that can be tapped in sudden, catastrophic releases. It stores energy, twists the crust, and powers bursts that outshine whole galaxies. Even the space around it is altered, because charged particles cannot move freely there. In a magnetar's neighborhood, motion is forced into tight spirals along field lines, like rails you cannot leave. Ordinary neutron stars can be fast pulsars with stable beams and predictable timing. Their emission is often powered by rotation and by particle winds in magnetospheres. They lose spin energy gradually, like a flywheel giving up speed over millennia. Magnetars are different because magnetic energy dominates their budget and behavior. They spin down quickly, flare unpredictably, and change their pulse shapes abruptly. They are not just lighthouses. They are stressed objects that crack and snap, and their emissions carry the signature of that strain. When their timing stutters, it is not a minor glitch. It is evidence that the star's interior and crust are rearranging under forces we barely reproduce in theory. This chapter begins with the distance stakes because distance is the only shield. A magnetar does not need to aim a rock at Earth. It only needs to radiate, and for the radiation to arrive with enough intensity. The key question is how close is too close for a biosphere like ours? A rough threshold often cited is about 1,000 light-years for severe damage. That number is not magic. It depends on beaming, spectrum, and total energy, and on how long the flare persists. It depends on whether the burst is a short spike or a longer tail. It depends on how Earth's atmosphere converts high-energy photons into chemistry. The same energy can be less dangerous if it is spread out, and far worse if it is concentrated. But it gives a scale. Inside that radius, the risk becomes existential, because recovery times stretch beyond ecological patience. Beaming complicates the story because magnetars do not radiate equally in all directions. Some flares are partly collimated, and the worst case is a beam crossing Earth. A beam can turn a distant event into a local catastrophe in a single second. In visual terms, it is the difference between a bulb and a spotlight sweeping the room. Spectrum matters because gamma rays penetrate and ionize differently than softer X-rays. Hard photons punch deeper into the upper atmosphere, and they create more ion pairs per unit energy. Atmospheric effects matter because ozone loss is a multiplier, not a single hit. The initial flash can be brief, yet the ultraviolet exposure can last for years. So the danger is not only the moment of impact, it is the aftermath, an extended season of harsh light, when DNA damage accumulates faster than ecosystems can adapt. We also need a reality check. The nearest known magnetar is about 9,000 light-years away. That distance is our margin of safety for now under current catalogues. It does not guarantee safety forever because catalogues are incomplete. Dust hides objects, and the galactic plane is crowded with confusing signals. Radio sources overlap, X-ray backgrounds glow, and distance estimates carry uncertainty. A magnetar can be quiet for long stretches, then announce itself with one burst. If it is on the far side of dense gas, we may miss it until it erupts. And when it erupts, the first message is already traveling at light speed. Magnetars were not found because they were easy to see. They were found because they misbehaved in ways other neutron stars rarely do. astronomers notice sudden bursts of X-rays and gamma rays from fixed sky positions. They notice timing irregularities, glitches, and spin changes that broke simple models. They noticed repeating soft gamma repeater events that suggested a new engine. Historically, these detections rode on the rise of space-based astronomy, when detectors finally escaped Earth's absorbing air. Early gamma-ray monitoring was built for security and science at once, and it kept stumbling onto cosmic surprises. From those clues, a picture formed. A neutron star with a field gone feral, releasing energy in spasms rather than steady beams. Rarity is part of the threat and part of the mystery. Magnetars are thought to be born in a fraction of core collapse supernovae. Their most active phase may last only thousands to tens of thousands of years. That is short on cosmic timescales, which makes them statistically elusive. A galaxy can host many neutron stars, yet only a few magnetars flare loudly. Even when they exist, they may be misclassified until a burst forces the issue. So we build nets of satellites and detectors to watch for transients. We rely on wide-field monitors, timing arrays, and rapid alerts across observatories. The sky is not static. The danger is in events that do not repeat on schedule, and in sources that only reveal themselves after years of silence. The investigative path of this series follows the evidence, then the physics. We start with observations and historical bursts that reached us across deep space. We track how magnetars reveal themselves through light curves and pulse periods. We connect those signatures to the internal stresses of a neutron star crust. We ask what a magnetic field does when it's strong enough to alter matter. Then we return to Earth and translate distant energy into local atmospheric outcomes. In other words, we follow the chain from a crack in a star to a change in sunlight. A magnetar's power source is stored magnetic energy that can be released suddenly. The crust can shift in a starquake when magnetic stresses exceed the lattice strength. That shift can rearrange the external field and accelerate particles in the magnetosphere. The result is a flare, often with a sharp initial spike and a softer tail. The spike can be so intense that instruments saturate, leaving only lower limits and damaged channels. In the biggest events, the spike can saturate detectors designed for nuclear tests. The tail can pulse at the star's rotation period, like a ringing bell. Those pulses are not decorative. They map the star's spin and magnetic geometry, and they reveal how the trapped fireball cools and leaks energy. The most famous reminder came on December 27, 2004. A magnetar called SGR 1806-20 produced a giant flare. It was about 50,000 light-years away, on the other side of our galaxy. Even at that distance, the flash affected Earth's upper atmosphere. It caused measurable ionization and disturbed radio propagation in the ionosphere. Some spacecraft instruments were overwhelmed, and the event rewrote hazard estimates. For a moment, the planet's high-altitude electrical layers behaved as if the sun had erupted directly overhead. If that flare had happened within 1,000 light-years, the story could be different. It would not need to be aimed with intent. Geometry alone could be enough, and the atmosphere would do the killing quietly. This is where the cosmic horror framing becomes a scientific problem. The universe can deliver extinction-level stress without a collision or a blast wave. A magnetar flare is silent at the ground, yet violent in the air above us. It attacks the shield we forget we have, and it does it at light speed. There is no evacuation from a photon front. There is only prior distance and the luck of not being in the beam. The unsettling part is how ordinary the sky can look while the damage accumulates. So the central question sharpens into a measurement problem. What makes magnetars uniquely lethal on cosmic scales compared with other stars? How do field strength, flare energy, and beaming translate into a kill radius? How often do giant flares occur, and how many magnetars might be undiscovered? How safe are we, given what we can detect and what we might miss? These are not abstract questions. They determine whether the galaxy contains rare fireworks or rare disasters with long shadows. To answer that, we need to understand what a magnetic field means at 1015 Gauss. In that regime, electrons move in quantized spirals and atoms deform under pressure. The field sets preferred directions, and matter becomes anisotropic, meaning it behaves differently depending on orientation. Vacuum itself behaves differently, and light can split into polarization modes. These are not poetic claims. They are predictions of quantum electrodynamics, where empty space can act like a medium under extreme fields. A magnetar is where astrophysics forces those predictions into observable consequences. When we watch a flare's spectrum and polarization, we are testing physics that cannot fit inside a laboratory. We also need to understand birth, because origin sets the initial field. Magnetars likely form in supernovae where rotation and convection amplify fields. In the collapsing core, turbulent motion can wind magnetic lines tighter, like twisting a rubber band until it stores energy. Some may come from massive progenitors, some from mergers, and some from chance. Their remnants can be traced in expanding shells and in hot young environments. But many are isolated, and their birth sites fade before we connect the dots. Supernova remnants disperse, star clusters drift, and the trail becomes statistical rather than photographic. So we reconstruct histories from timing ages, from associations, and from population models. We compare spin-down rates to estimate how long they have been losing energy, even when their true ages remain uncertain. The opening scenario was not a prophecy. It was a boundary condition. It shows what happens when a magnetar flare intersects a living planet. The details depend on energy and distance, but the mechanism is robust. High-energy photons ionize air, chemistry shifts, ozone drops, ultraviolet rises. The planet can look intact from space, while its surface becomes hostile. It is an apocalypse without ruins, and that is what makes it hard to imagine. What would civilization do if the infrastructure survived, but the outdoors became dangerous for years? Our margin of safety rests on what we know and what we do not. The nearest known magnetar at about 9,000 light-years is far beyond the worst zone. Yet the galaxy is large, dusty, and full of compact remnants we have not catalogued. The nets of detectors reduce surprise, but they cannot eliminate it. They watch for bursts, but they cannot stop a burst already in flight. They can only tell us what happened and help us estimate what could happen again. That is both comforting and unsettling. Comfort in knowledge and unease in the limits of knowledge. This chapter marks the perimeter of the problem and sets the scale of fear. Next we move inward, from the kill radius to the object that defines it. We follow a star's collapse into a neutron core, then into a magnetar's twisted field. We ask how a magnetic engine builds pressure until the crust fails and the sky erupts, and we keep one uncomfortable question in view. How close is close enough to end us? We leave Earth for now and go to the birthplace, where supernova debris still glows. From there, the story becomes a forensic investigation of the most extreme of magnets known. Distance is the only shield, but distance does not explain the weapon. To understand the kill radius, we have to build the object that can light it. That means starting long before any flare, inside a star that is still alive, still bright, and already doomed by its own success. A magnetar begins as a normal star, just heavier and less forgiving. It is massive enough that its core runs hotter, and it burns fuel with an urgency smaller stars never need. In the deep interior, gravity keeps raising pressure until fusion can keep up, and the balance holds for millions of years. The star looks steady from the outside, but inside it is climbing a ladder with missing rungs. Hydrogen becomes helium, helium becomes carbon, and the ladder continues upward. Carbon burns to neon and oxygen, oxygen burns to silicon, and silicon builds iron group nuclei. Each stage runs faster than the last because the fuel becomes harder to extract energy from. The core must climb to higher temperatures just to keep the lights on. The timescales shrink with every step, and that acceleration is a warning. Hydrogen burning can last millions of years, while silicon burning may last only days. The star is spending its savings at an increasing rate, and the account is finite. From far away, the star still shines, but the clock is now inside the chemistry. These late stages also rearrange the star into shells, like an onion built from nuclear ash. Hydrogen burns in an outer shell, helium burns deeper, and heavier elements burn closer to the center. Each shell has its own temperature and density, and each feeds the next with fresh fuel. When the core changes, the whole structure adjusts, and the star becomes a dynamic machine rather than a quiet sphere. Iron is the dead end because fusing it costs energy instead of releasing it. The binding energy per nucleon peaks around iron and nickel, so fusion beyond that point is an uphill reaction. The core becomes an iron ash heap supported mostly by electron degeneracy pressure. The star still shines, but the center is now a trap with a timer. Electron degeneracy pressure is a quantum rule masquerading as a force. Electrons cannot all occupy the same low-energy states, so they resist being squeezed into a smaller volume. That resistance does not depend on temperature, which is why the core can be hot and still behave like a stiff object. It is also why the support can fail abruptly, with almost no warning visible at the surface. When the iron core grows too massive, pressure fails in a sudden global way. The Chandrasekhar-like limit for the core is not a single number, because temperature and composition matter, but the idea is the same. Gravity wins and the core collapses in a fraction of a second. In that moment, the star's long life ends with a single mechanical decision. Collapse is not a gentle shrinking, it is a phase change in motion. The infalling matter accelerates to a significant fraction of a light speed, and the density rises through regimes that do not exist anywhere else. Electrons are forced into protons, making neutrons and flooding the core with neutrinos. This is neutronization, an atomic identity change driven by pressure. Those neutrinos are not a side effect, they are the dominant energy channel. For a brief time, the core is so dense that even neutrinos struggle to escape, and they diffuse outward like heat through fog. The inner core stiffens at nuclear density and rebounds, sending a shock outward. It is a bounce, but it is also a collision between physics domains. That shock initially stalls, because it loses energy breaking nuclei apart and lifting in falling layers. Photodisintegration consumes energy by tearing heavy nuclei into free nucleons, and the shock pays that cost immediately. Meanwhile, the outer core continues to rain down, adding weight and ram pressure. The explosion is not guaranteed, and the star can fail quietly into a black hole. In successful core collapse, neutrinos become the hidden engine. They carry away most of the gravitational binding energy, around 1053 ergs, and a small fraction heats the stalled shock. That fraction sounds tiny, but it is enough if it is deposited in the right place. Neutrino absorption and convection revive the shock and push it through the star. The revival is messy, and that mess matters. Convection and standing accretion shock instabilities can slosh the shock front, creating asymmetries that later show up in the remnant. In simulations, the shock does not always expand as a perfect sphere, and the star does not die symmetrically. The explosion is a three-dimensional argument between gravity, turbulence, and neutrino heating. The outer layers are expelled as a supernova, while the core is left behind as a compact remnant. The ejected material carries freshly forged elements, including oxygen, silicon, and iron group nuclei made in the final burning stages. It also carries radioactive isotopes, whose decay can power the visible light curve for months. A supernova is therefore both a death and a chemical broadcast. The debris field is not just aftermath, it is evidence. Supernova remnants expand as hot shells threaded with magnetic fields and enriched elements. Their shapes record asymmetries, jets, and the density of the surrounding medium. Their chemistry tells us what layers were ejected and which were swallowed. When a neutron star sits inside a remnant, the remnant becomes a forensic scene with a suspect still present. You can read the shock speed from X-ray temperatures, and you can map the distribution of elements with spectral lines. You can compare the remnant's age to the neutron star's timing age, and ask whether the numbers agree. Even the remnant's cavities and filaments can hint at the progenitor's wind history. Visually, remnants are not simple rings, and that complexity is part of the story. In X-rays, they glow like torn silk, with knots where the shock hits denser clouds. In radio, they trace magnetic fields, revealing arcs and loops that look like handwriting across the sky. In optical, thin filaments mark cooling gas, as if the explosion left behind bright scratches. The remnant core is a neutron star, a stellar corpse with a city-scale radius. Typical masses run about 1.4 to 2.3 times the Sun, packed into roughly 20 kilometers. The average density is near nuclear density, around 1014 to 1015 grams per cubic centimeter. Matter is no longer atoms in a lattice of chemistry. It is nuclei and neutrons under crushing pressure. It is difficult to keep the scale honest, so it helps to translate it. If you could compress a mountain into a teaspoon, you would still be far short of neutron star density. A cubic centimeter of neutron star material would outweigh 1 billion tons, and it would do so without any empty space. The star is not small because it is weak. It is small because gravity has won. Inside, the physics becomes uncertain in ways that are scientifically valuable. The equation of state of ultra-dense matter, how pressure relates to density, controls the radius for a given mass. That is why measuring neutron star radii is not just astronomy, it is nuclear physics. Every constraint is a clue about matter at densities beyond laboratory reach. Gravity at the surface is extreme, and it reshapes every process near it. The escape velocity is a significant fraction of the speed of light, often around 0.4 to 0.7 c, depending on mass and radius. Time runs measurably slower at the surface than far away, and light is gravitationally redshifted. Even photons climb out as if they are dragging weight. A small mountain on Earth becomes a trivial bump because the crust is held down by forces beyond terrestrial materials. The crust is only a kilometre or so thick, yet it supports stresses that would pulverise any rock we know. Beneath it, the star is mostly fluid, but it is a fluid of neutrons and exotic particles. The boundary between crust and core is a frontier, and magnetars live on that frontier. A neutron star is also born hot and fast, and it does not stay that way. In the first seconds, it is a proto-neutron star filled with trapped neutrinos and violent convection. It cools by neutrino emission, and it contracts as pressure support changes. The newborn object is shedding energy in a way that is almost invisible to us. Angular momentum conservation spins it up as it shrinks, like an ice skater pulling in their arms. If the progenitor core rotated modestly, the remnant can still end up fast. The newborn object can rotate in milliseconds, and that rotation stores an enormous reservoir of kinetic energy. In some scenarios, that reservoir competes with the magnetic one. Rotation turns neutron stars into clocks, and clocks become diagnostics. Many neutron stars emit beams from magnetic poles, and the beam sweeps past Earth like a lighthouse. We see pulses at the spin period, from milliseconds to seconds, depending on age and torque. The regularity is so precise that it can rival atomic standards over long stretches. The lighthouse picture is simple, but the mechanism is rich. A rotating magnetized conductor induces huge electric fields, and those fields pull charges from the surface. The charges accelerate along open field lines, emitting radio waves and high-energy photons. Pair production can fill the magnetosphere with electrons and positrons, turning the star into a self-sustaining particle accelerator. We measure those periods with radio telescopes and high-energy timing instruments. We measure their slow change over time, the spin-down rate, by comparing pulse arrival times over months and years. The technique is called pulsar timing, and it is essentially celestial bookkeeping with exquisite precision. A tiny drift in phase can reveal a torque you cannot see. Timing is not just bookkeeping, it is a way to weigh invisible forces. A stable pulsar can be predicted like a metronome, and deviations carry meaning. The period derivative tells us the loss of rotational energy and the strength of braking torques. Under the simplest magnetic dipole model, a larger spin down implies a stronger surface magnetic field. That estimate is crude, but it gives a first map of the population. It assumes a dipole geometry, a vacuum-like magnetosphere, and a particular angle between spin and magnetic axes. Real neutron stars violate all of those assumptions to some degree, yet even an imperfect map can separate ordinary pulsars from the outliers. Historically, those outliers arrived as surprises. Pulsars were discovered in 1967, and within a few years, neutron stars became a working reality rather than a theoretical end state. Magnetars came later, identified through soft gamma repeaters and anomalous X-ray pulsars that did not fit the rotation-powered template. The classification changed as instruments improved, and the monster slowly took shape. Most neutron stars live as ordinary pulsars, powered mainly by rotation. They radiate because a rotating magnetic field accelerates charges and drives winds. Their energy budget is the flywheel of spin, and it drains gradually. Their magnetic fields are strong by human standards, around 1011 to 1013 Gauss, but they are not usually explosive. They can glitch and wander, yet their long-term behavior is often steady. A glitch is a sudden spin-up, often interpreted as an exchange of angular momentum between the crust and a superfluid interior. The details are still debated, which is part of the fascination. Even in ordinary pulsars, the interior is not a settled subject. A magnetar is the upgrade, where magnetic energy dominates everything else. Its inferred dipole field is typically 1014 to 1015 Gauss, and internal fields may be higher. It spins more slowly than many pulsars, often a few seconds, yet it shines in X-rays. That brightness cannot be explained by rotation alone, because the spin-down power is too small. Something else is paying the bill, and the field is the only reservoir large enough. Magnetars can show persistent X-ray emission that decays and rises as if the star is breathing heat through its crust. Their spectra can include hard tails, suggesting non-thermal processes in the magnetosphere. In plain terms, the star is luminous because it is magnetically stressed. The monster question becomes a birth question. How does a collapsing star produce a field so large that it can later weaponize radiation? Several hypotheses compete, and each leaves different fingerprints in the sky. None is fully proven because we cannot watch the field assemble inside an opaque explosion. We infer origins from populations, environments, and the physics of collapse. We look for magnetars in young clusters, in supernova remnants, and in regions where massive stars recently died. We compare their velocities and locations, and we ask whether they are consistent with a violent birth kick. Every association is a clue, but every association can also be coincidence. The first idea is magnetic flux conservation, sometimes called flux freezing. If magnetic field lines are locked into the conducting plasma, collapse squeezes them tighter. The surface area shrinks by many orders of magnitude from a stellar core to a neutron star. If flux is conserved, the field strength rises as the inverse of area. A modest progenitor field can be amplified into a pulsar field, and a strong progenitor field could reach magnetar levels. This scaling is easy to state, which is why it remains attractive. It also connects magnetars to a known population of magnetic massive stars, which have surface fields measured in kilogauss. The question is whether those fields reach the core, and whether they survive the collapse intact. Flux freezing is attractive because it uses a simple scaling, but it has limits. It requires the progenitor core to already carry a very strong field, perhaps like those in rare magnetic massive stars. It also assumes the field geometry survives collapse without being shredded by turbulence. Collapse is violent, and turbulence does not respect tidy lines. Observationally, magnetars are rare compared with neutron stars, which fits a rare progenitor channel. Yet not all magnetars are found near the most massive stars, which complicates a single origin story. Some appear in environments that suggest more ordinary progenitors, or at least progenitors that were not extreme in obvious ways. That tension is a reminder that we see the end product, not the assembly line. The second idea is a convective dynamo in a rapidly rotating proto-neutron star. In the first seconds, convection and differential rotation can be extreme. Hot material rises, cooler material sinks, and rotation twists those flows into helices. If the spin is fast enough, turbulent motions can organize into large-scale fields. The dynamo can wind and amplify magnetic fields until they approach equipartition with kinetic energy. Equipartition means the magnetic energy density becomes comparable to the energy density of the moving fluid. At that point, the field is no longer a passive tracer, it pushes back on the flow. The system becomes self-limiting, but the limit can be magnetar strength. The dynamo route makes a sharp prediction about rotation at birth. It prefers a newborn neutron star spinning in a few milliseconds, because rapid rotation feeds the dynamo. That fast spin should inject extra energy into the supernova, and possibly make it unusually bright. It could also drive jets, or at least produce more asymmetry than a typical explosion. Some superluminous supernovae and hypernova-like events are modelled with magnetar engines. In those models, the magnetar's rotational energy is tapped and converted into radiation as the ejector expands. The light curve becomes a signature of a central power source, rather than radioactive decay alone. Yet many magnetars are associated with ordinary-looking remnants, which challenges a universal fast spin requirement. The third set of ideas involves mergers and fallback, where birth is not a single clean event. Two neutron stars can merge and leave a massive, rapidly rotating remnant for a short time. That remnant can host enormous magnetic amplification through shear and turbulence. The shear layers behave like a blender, generating small-scale fields that can cascade into larger structures. If it avoids prompt collapse to a black hole, it could become a magnetar-like object. This channel also connects magnetars to gravitational wave events and kilonovae, at least in principle. The connection is compelling because we now detect mergers directly, and we can watch the aftermath across the spectrum. The open question is how often the remnant survives long enough to matter. Fallback scenarios keep the core collapse setting, but add late-time accretion. After the explosion begins, some ejected material can fail to escape and fall back. That returning matter can form a disk, or it can rain down more directly, depending on angular momentum. Accretion can bury magnetic fields, then allow them to re-emerge as the crust evolves. Fallback can also torque the star and change its spin history. It can spin the star up or down, and it can alter the magnetosphere by loading it with plasma. Evidence is mixed, because fallback is hard to measure directly, and remnants evolve in messy environments. Still, fallback is a natural consequence of marginal explosions, so it remains difficult to ignore. Each hypothesis has supporting clues and missing pieces. Associations with young star clusters suggest massive progenitors for some magnetars. The short characteristic ages inferred from spin down suggest youth, but characteristic age can be misleading. It assumes a constant breaking law, while magnetars often change their torque dramatically. Proper motion can separate a magnetar from its birth remnant over thousands of years. A fast kick can move the neutron star far from the explosion center, and the remnant can fade or blend into the galactic background. Some magnetars sit in or near remnants, others appear isolated in crowded galactic fields. Isolation may be real, or it may be a limitation of what we can see. Timing again becomes a tool because magnetars do not behave like quiet clocks. Their periods are seconds, but their spin-down rates are large and noisy. They show glitches, sudden spin-ups, and episodes of enhanced torque. Their pulse profiles change, sometimes in step with bursts and flares. The timing noise suggests that magnetospheric currents and internal changes are actively reshaping the braking torque. In a simple pulsar, the torque is relatively stable, and the magnetosphere is close to a steady state. In a magnetar, the magnetosphere can be twisted, untwisted, and reloaded with plasma. The star's clock is therefore a seismograph for magnetic weather. The key difference is the energy budget stored in the magnetic field itself. Magnetic energy density scales as b squared over 8 pi in CGS units. For b around 1015 Gauss, the energy density is enormous, around 1028 to 1029 ergs per cubic centimeter. Multiply by a neutron star volume of order to 1018 cubic centimeters, and you get 1046 to 1048 ergs. That is enough to power repeated bursts and rare giant flares. It is also enough to heat the crust, drive persistent X-ray emission, and maintain a magnetosphere full of currents. The field is not just a number measured by timing, it is a reservoir that can be tapped. When the reservoir is large, the star can afford to be violent. This order of magnitude is why magnetars can be lethal at distance. A giant flare can release 1044 to 1046 ergs in seconds, with a hard initial spike. If even a fraction is beamed, the apparent energy along the beam can be higher. The radiation is not stopped by interstellar space, it only dilutes with distance. The same physics that makes a magnetar bright also makes it a potential biosphere hazard. High-energy photons can ionize an atmosphere, break molecular bonds, and trigger chemical cascades. Even if the surface life is shielded by rock or ocean, the sky itself can change, and that matters for climate and habitability. The danger is not a blast wave, it is a flash of altered chemistry. Magnetic energy is not released smoothly, because the star is a stressed solid over a fluid interior. The crust is a lattice of nuclei under extreme pressure, and it can store elastic strain. Beneath it, superfluid neutrons and superconducting protons may carry magnetic flux in quantized structures. The interior field can drift, tangle, and push, and the crust must respond. Internal fields can twist and drift, pushing against that crust. When stress exceeds the yield strength, the crust can crack or slip in a starquake. The word quake is metaphorical, but the physics is real. A sudden rearrangement of stress in a brittle layer. The external magnetic field can then reconfigure, launching waves and accelerating particles. That external region is the magnetosphere, and it is where stress becomes radiation. It is filled with plasma tied to field lines and driven by currents. Twists in the field store energy like a wound spring, and reconnection can release it abruptly. In a reconnection event, field lines change partners, and magnetic energy becomes heat and motion. The magnetosphere can trap a hot pair plasma fireball that cools and pulses at the spin period. Those pairs, electrons and positrons, scatter photons and shape the observed spectrum. The trapped fireball can last for minutes in a giant flare tail, and the pulses act like a rotating beacon. The star's rotation stamps a rhythm onto the aftermath. This is the stage where the next chapter will focus, because it is where bursts are made. Yet it helps to picture the environment before we enter it. Imagine field lines arcing out like taut cables, anchored into a crust that is trying not to break. Imagine a volume where quantum electrodynamics becomes practical, and vacuum itself can behave like a birefringent medium. Before we go there, we need to know how we catch these events at all. Magnetars are transient and their most dangerous behavior is brief. A radio telescope can time pulses and measure spin, but many magnetars are radio quiet most of the time. Some switch on only during outbursts, as if the magnetosphere temporarily becomes transparent to radio emission. X-ray observatories can see persistent emission and outbursts, and they can track spectral changes. They can measure thermal components from the surface and non-thermal components from magnetospheric scattering. They can also watch hotspots appear and fade, which hints at where energy was deposited in the crust. In magnetars, the surface is a map of stress. Gamma-ray monitors can catch the initial spikes of giant flares, even when other instruments saturate. Those spikes rise in milliseconds, which is faster than most satellites can react. Detectors designed for wide-field monitoring become the first witnesses, and their data can be messy but decisive. Sometimes the best measurement is simply that something happened and where. These observational nets matter because magnetars do not announce themselves politely. Wide-field gamma-ray detectors provide triggers and sky localizations within seconds. X-ray satellites can sleuth for follow-up, measure afterglows, and refine positions. Radio arrays can search for transient pulses and measure dispersion through the interstellar medium. Optical and infrared telescopes can look for associated remnants, clusters, or dust-obscured counterparts. In the infrared, you can see through the galactic plane's dust lanes, where many magnetars live. In optical, you can sometimes measure proper motions though the targets are faint. Each band adds context, and context is how you separate a real association from a coincidence. Multi-messenger coverage is not a slogan, it is a practical defense against blind spots. Timing gives spin and spin down, spectra give temperatures and scattering environments. Polarization can test quantum electrodynamics in strong fields, if instruments are sensitive enough. In ultra-strong fields, photon propagation can be altered, and polarization becomes a diagnostic rather than a detail. Gravitational waves could connect magnetar-like remnants to mergers, though the link is still developing. Neutrinos are expected from core collapse, but only a nearby event would be detectable. The lesson is that the universe does not provide a single clean channel for evidence. We build a network because any one instrument can miss the crucial seconds. Supernova remnants remain the slow archive, while bursts are the fast alarm. Remnants tell us where and how a neutron star was born if the association is secure. Proper motions and distances can confirm whether the neutron star and shell share a history. Element abundances and expansion ages can constrain explosion energy and progenitor mass. In some cases, a magnetar sits in a remnant that looks ordinary, which forces models to allow magnetars without extreme supernova signatures. That is an important constraint, because it suggests magnetar formation may not require a spectacular explosion every time. It may require special interior conditions that do not always broadcast themselves. The monster can be built quietly, then reveal itself later. The tension in this origin story is that small differences at birth can decide everything. A slightly faster spin can enable a dynamo that runs away. A slightly stronger seed field can be amplified by collapse into a different regime. A bit more fallback can bury or reshape the field and change early spin down. Two stars that look similar on the main sequence can leave remnants with radically different futures. That observation is unsettling, because it implies that the threat is not easily predicted from surface appearances. The decisive physics may happen in the last seconds, behind layers we cannot see. In astronomy, the most important events are often the least observable. One path makes a quiet pulsar, a stable lighthouse with predictable timing. Another path makes a magnetar, where the field becomes a loaded spring. Both are neutron stars, both are compact and dense, and both are born in supernova violence. The difference is which reservoir dominates after the explosion ends. Rotation makes a long-lived clock, magnetism makes a short-lived catastrophe engine. In ordinary pulsars, the spin energy bleeds away over millions of years, and the star gradually dims. In magnetars, magnetic decay and rearrangement can dominate within tens of thousands of years. The timeline of danger is therefore compressed, but the intensity is higher. This is where the central question returns, now with sharper edges. What makes magnetars uniquely lethal is not just field strength, it is how that field stores and releases energy. The kill radius depends on flare energy, spectrum and beaming, but the source is the same reservoir. If magnetars are born from rare conditions, then the threat is rare but real. If they can form through multiple channels, then the galaxy may host more of them than we expect. That possibility changes how you think about risk because it changes the denominator. How many magnetars are quiet right now, hidden behind dust, waiting for a flare that lasts less than a second? How many have already flared long before humans could notice? Our uncertainty is not only theoretical, it is observational. We find magnetars when they flare, and quiet ones can hide in dust and confusion. We estimate distances with imperfect methods, and energy with instruments that sometimes saturate. We infer magnetic fields from timing models that assume simple geometries. Every step adds error bars, and error bars matter when the stakes are planetary. A factor of 2 in distance becomes a factor of 4 in inferred energy, and a factor of 4 changes the hazard radius dramatically. The difference between a near miss and a direct hit can be a few kiloparsecs. In a galaxy this large, that is both a lot and not much. Still, the outline is clear enough to be unsettling. Massive stars build iron, iron triggers collapse, and collapse makes neutron stars. Some neutron stars are born with magnetic fields so intense that they dominate their evolution. Those fields store 1046 to 1048 ergs, enough to power giant flares across the galaxy. The magnetosphere is where that stored stress turns into radiation that can cross interstellar space unchanged. Space does not absorb much gamma radiation, and it does not soften the blow. It only spreads the photons out over a larger sphere, and that is the only mercy built into the geometry. Distance is the shield, but it is a shield you cannot carry. Next we move inward, from the birth physics to the failure modes. We follow magnetic stress from the interior into the crust, then out into the magnetosphere. We track how a twist becomes a burst, and how a burst becomes a planetary hazard. The monster is built at birth, but it becomes terrifying when it finally snaps. This chapter ends at the edge of the magnetosphere, where the field stops being a number and starts being an environment. The next chapter begins where charged particles are trapped and where light is manufactured by violence. The question is no longer how a magnetar forms, but how it fires. A magnetar is not dangerous because it is massive, since many stars are massive and still harmless at distance. It is dangerous because its magnetic field becomes a stored weapon, an invisible reservoir, and the weapon can fire as light. That light is not gentle starlight either, but hard radiation that can ionize, dissociate, and cascade through air. The central question stays fixed as we move closer to the source, because the stakes do not change. What makes magnetars uniquely lethal on cosmic scales, and how close is close enough to threaten Earth? Distance is not a simple shield when the emission is hard, fast, and sometimes narrowly directed. Chapter 1 framed the kill mechanism as chemistry driven by radiation at distance, where photons rewrite atmospheric molecules. Chapter 2 built the monster's engine as magnetic energy trapped in a neutron star, compressed into a sphere the size of a city. Now we enter the region where that energy becomes observable physics, and sometimes becomes catastrophe. Here, the story becomes less about what we fear, and more about what instruments can actually measure. Start with anatomy, because structure controls behavior and behavior leaves signatures in data. A magnetar's magnetosphere is the space where magnetic field lines guide plasma and photons, shaping what can escape. It is not empty, and it is not passive, because currents, radiation, and pair creation can fill it. Even the word sphere is misleading, because the magnetosphere is a dynamic volume with preferred directions. Visually, imagine a black sphere with a thin, bright skin wrapped in luminous arcs that loop and flare like frozen lightning. Those arcs are not decorative. They are the geometry of force, and they decide where particles can move. If we could see magnetic stress, it would look like tensioned threads pulling on the star's surface. Near the star, many field lines are closed and loop back to the surface, forming magnetic cages. Plasma trapped on these loops can circulate and scatter radiation, shaping what we see from far away. Farther out, other lines open and extend outward, feeding a wind and carrying angular momentum away. The open lines are not just exits, but conduits that connect the star to interstellar space. That split between closed and open lines matters for both emission and torque. which is why timing and brightness often change together. Closed regions store energy and trap particles, while open regions connect to space and control spin down. When the boundary shifts, the star's timing and brightness can change in the same week. In the data, that can look like a star changing its personality without warning. In ordinary pulsars, the magnetosphere is often modelled as near steady, like a lighthouse with a stable beam. In magnetars, steady is rare because the field can be twisted by internal evolution and crustal motion. A twist means the external field is sheared away from a simple dipole, like a cable wound tighter than it wants. The twist is also a promise that something is being stored and that storage can be released. A dipole is the clean textbook picture, with north and south and smooth loops. Magnetars rarely grant us that simplicity. Their fields can be multipolar near the surface, with smaller loops nested inside larger ones, and that complexity matters for where stress concentrates. The smallest loops can be the sharpest knives, because they focus gradients and concentrate current. Twist is not just geometry, it is electric current, and current is stored energy in motion. A twisted magnetosphere requires currents flowing along field lines to support the shear against magnetic tension. Those currents are carried by electrons, ions, and often electron-positron pairs created by high-energy photons. In practice, the magnetosphere becomes a circuit, with the star acting as both battery and load. Pairs matter because the environment is so extreme that the magnetosphere can supply its own charge carriers. When gamma rays interact with the field, they can convert into matter and antimatter, replenishing the current. In plain terms, the magnetosphere can manufacture the particles it needs to keep the twist alive. The result is a self-sustaining plasma that can thicken quickly after a disturbance. Currents do work on the star, and the star does work on the currents, so the system is a feedback loop. Returning particles slam into the surface and heat it, creating hotspots and raising the persistent X-ray output. That heating can be mapped through spectra and pulse profiles, because the star rotates and the hot regions move in and out of view. Over time, those hotspots can drift, widen, or fragment as the current pattern evolves. For visuals, the surface becomes a rotating map of heat, with one or two bright patches drifting across a dark hemisphere. Each rotation turns that map into a pulse train, and each pulse carries information about geometry. Even the shape of a pulse, sharp, broad, double-peaked, can reveal how the hot region is arranged. A slight asymmetry in the pulse can be the signature of an offset field or a lopsided twist. A twist also changes how photons escape, because it thickens the magnetosphere with scattering charges. Resonant scattering in the magnetosphere can upscatter soft thermal photons into harder X-rays, shifting energy upward. The result can be a spectrum with a thermal component plus a hard tail, which is a fingerprint of magnetospheric processing. That hard tail is not a separate engine, but the same light reshaped on its way out. Resonant means the scattering is selective, tuned to the cyclotron frequency set by the magnetic field. Photons interact most strongly where their energy matches that resonance in the local field, so the magnetosphere becomes a layered filter. In effect, the star's light is being reprocessed as it climbs out. The reprocessing can also be phase-dependent, because different field regions rotate into view. This is where measurable consequences keep the story honest, because magnetars are not explained by metaphor alone. We do not infer twist only from theory. We infer it from changing pulse shapes and changing spectral hardness. We also infer it from torque noise, since a loaded magnetosphere changes the braking force. In some sources, a hardening spectrum and a torque change arrive together, like two clocks striking at once. Torque is the lever arm of the magnetic field, and the lever can lengthen or shorten as open field lines change. When the magnetosphere is more heavily charged, it can carry away more angular momentum. The star's rotation then slows in a way that tracks magnetospheric state. If you listen long enough, the spin becomes a seismograph for invisible currents. A magnetar's field is so strong that it pushes beyond classical electrodynamics, where empty space is assumed to be inert. Quantum electrodynamics predicts a critical scale where the vacuum itself responds, because virtual particles become polarized. That scale is the Schwinger critical field, about 4.4 times 10 to the 13 Gauss. It is a threshold where nothing stops behaving like nothing. At that threshold, the energy spacing of electron motion in a magnetic field reaches the electron rest mass, so quantum effects stop being small corrections. Virtual particle pairs in the vacuum become easier to polarize, and the vacuum behaves like a medium with optical properties. Magnetars exceed this field, so the effect is not a detail, it is part of the environment. In other words, the vacuum becomes an active participant in how light travels. Historically, this regime was predicted long before magnetars were confirmed as a class. In the mid-20th century, QED was built to explain how light and matter interact at high energies. Magnetars later became a natural laboratory, because no Earth-based magnet can approach these field strengths. When soft gamma repeaters were first catalogued, their behavior looked like a new kind of storm before it looked like a new kind of star. One key prediction is vacuum birefringence, a subtle but profound effect on light. Light propagating through the magnetized vacuum splits into polarization modes that travel differently, as if space itself were a crystal. The vacuum acts like a birefringent medium, and polarization becomes a probe of field strength and geometry. It is a way to see the field without touching it. In a visual sense, imagine a beam leaving the surface and passing through invisible layers that twist its orientation. The light is the messenger, and the vacuum is no longer transparent in the classical way. It is transparent, but it is structured. The structure is not made of matter, but of quantum response. This is testable, which is why it matters for a documentary about real objects rather than speculative ones. X-ray polarimeters can measure the polarization fraction and angle across pulse phase, tracking changes as the star rotates. If the polarization follows the rotating field geometry in the predicted way, QED is being verified in a regime no lab can reach. The star becomes a calibration source for fundamental physics. The measurement is difficult because X-ray polarization is a faint signature, and detectors must count many photons. Yet the reward is direct evidence that the vacuum is behaving as theory says it should. It is an experiment performed by nature, with a neutron star as the apparatus. Each pulse is another trial, and the rotation supplies the controlled change in viewing angle. Polarization is also a practical diagnostic of Magnetar structure, not just a trophy for fundamental physics. It can separate surface thermal emission from magnetospheric scattering, because each produces different polarization signatures. It can also constrain whether the field is mostly dipolar or strongly multipolar near the surface. That matters because multipoles change where stress accumulates and where failure may begin. A dipolar field tends to produce a smoother, more predictable swing in polarization angle across the pulse. Strong multipoles can create abrupt changes because the local field direction shifts rapidly across the emitting region. In other words, polarization can sketch a map of magnetic complexity. It is not a photograph, but it is a contour map drawn in light. QED effects do not stop at polarization, because they affect radiative transfer and the survival of high-energy photons. In ultra-strong fields, photon splitting and modified scattering cross-sections can alter spectra, especially in the hard X-ray band. These processes can soften or reshape high-energy emission, changing how bursts look to detectors. They can also change what fraction of the flare's power escapes as the hardest gamma rays. Photon splitting is exactly what it sounds like, and it is alien to everyday intuition. A single photon can divide into two lower energy photons in the presence of a strong field, conserving energy and momentum through the field's influence. The result is that the magnetosphere can damp the hardest radiation before it escapes. It is as if the star has a built-in spectral limiter, though it is not always strong enough to prevent danger. Now shift from vacuum to matter, because magnetars dominate both, and the surface is where the two meet. Under extreme magnetic fields, atoms do not stay round, because the electron wave functions are squeezed and reshaped. The electron cloud is squeezed sideways and stretched along the field, making elongated atoms and chain-like molecular structures. The surface becomes a place where solid and gas are not as familiar as they sound. This is not a small distortion. The magnetic field can become comparable to the Coulomb force that binds electrons to nuclei, so chemistry is rewritten. The periodic table still exists, but the rules that determine size, bonding, and opacity are altered. Even a thin atmosphere, only centimeters thick in scale height, can control what we see in X-rays. Electron motion perpendicular to the field becomes quantized into Landau levels, which are discrete energy states. Instead of a continuous range of energies, electrons occupy specific steps, like floors in a building. That changes how matter absorbs and emits photons, especially in X-rays where the relevant energies live. It also means the atmosphere can imprint sharp features if conditions allow them to survive scattering. Landau quantization also changes how electrons contribute to pressure and conductivity. It can make transport strongly directional, with heat flowing more easily along field lines than across them. That anisotropy matters because it can shape surface temperature patterns over time. A warm region can persist longer if heat is trapped from spreading sideways. The quantization changes opacity, which changes what a surface looks like to a distant telescope. A Magnetar atmosphere can become anisotropic, with different transparency along and across the field depending on polarization mode. The anisotropy feeds directly into pulse profiles, because beaming depends on direction. The star's flashlight pattern is written by microphysics. Visually, the surface emission is not a simple glow. It is a textured pattern of beams and shadows, shaped by magnetic direction and scattering. As the star turns, those beams sweep past our line of sight and create the pulse. If we could hover above the surface, we would see brightness sliding along field-guided lanes. Spectral lines and absorption features can also shift or appear under these conditions, though they are often subtle. Cyclotron features can mark the local field strength, because charged particles spiral in magnetic fields at a characteristic frequency. In magnetars, they can be complicated by vacuum effects and scattering, which can smear or hide the line. Even a tentative feature can still be valuable, because it anchors the field strength to a specific region. Even when lines are weak, the continuum shape can still carry the imprint of altered opacity. A slightly harder tail, a suppressed high-energy component, or a phase-dependent temperature can all hint at the same physics. The atmosphere and magnetosphere together become a coupled radiative system. What we detect is the final product of several layers of processing. The key point is that the field is not only a force on charged particles, like a giant bar magnet scaled up. It is a rule set that rewrites atomic structure, radiative transfer, and the meaning of empty space. That is what it means to almost break reality, because the familiar approximations stop working. The universe is still lawful here, but the laws are operating at their limits. Yet the story stays anchored to measurement, because magnetars are not philosophical objects. We measure their spectra, we measure their pulse shapes, and we measure how those change after bursts. We use those changes to infer where energy was deposited and how the magnetosphere reorganized. The star leaves fingerprints, and the job is to learn how to read them. After a burst, the spectrum can harden, then soften over days or months, suggesting a twist that gradually relaxes. The pulse profile can morph as hotspots expand or fade, implying changing surface heating. These are not guesses, they are patterns repeated across multiple sources. The relaxation is slow enough to watch, like cooling metal after a brief violent strike. Now connect the magnetosphere back to the interior, because stress must travel through matter before it can erupt into light. Magnetic fields are anchored in the crust and threaded through the core, and the star is not a rigid body. When the internal field evolves, it pushes on the crust, and the crust pushes back until it cannot. The magnetosphere may look like the stage, but the interior is the machinery beneath it. The crust is only a kilometre or so thick, but it carries enormous responsibility. It is the boundary between a superdense interior and a magnetosphere that can rearrange violently. It is also a brittle solid in a place where solids are not supposed to survive. Under that crust, pressure and density are so high that matter becomes an exotic fluid of nuclei and degenerate particles. There are several pathways for releasing magnetic energy into radiation, and each leaves a different kind of signature. One is crustal yielding, where the solid lattice slips or fractures under magnetic stress, releasing energy and changing the field's anchoring. Another is magnetic reconnection in the magnetosphere, where field lines rearrange and convert field energy into heat and particle acceleration. The difference is partly location and partly timescale. A third pathway is wave transport, especially Alphen waves, which are the natural vibrations of a magnetized plasma. An Alphen wave is a disturbance that travels along magnetic field lines, carrying energy and momentum like a plucked string. In magnetars, cross motion can launch Alphen waves into the magnetosphere, where they can dissipate and accelerate particles. The wave is a messenger that carries a quake into space. Alphen waves matter because they provide a bridge between slow crustal motion and fast radiative response. The crust may shift over milliseconds to seconds, but the wave can carry that disturbance outward at a substantial fraction of the speed of light. The magnetosphere then responds quickly, and the sky sees a flash. That speed is why cause and effect can look almost simultaneous to a distant observer. These pathways are not mutually exclusive, and that matters for interpreting light curves and afterglows. A crustal slip can trigger reconnection, and reconnection can feed back on the crust through changing stresses. The observed burst can be the surface of a deeper coupled system. When we see a spike and a tail, we may be seeing multiple mechanisms layered in time. Reconnection is central because it can be fast, and speed is what makes a flare feel like an explosion. When twisted field lines become unstable, they can snap into a lower energy configuration, converting magnetic energy into particle energy. The released energy heats plasma, creates pairs, and produces hard X-rays and gamma rays in milliseconds. In that instant, the magnetosphere behaves less like a halo and more like a detonator. In visual terms, the magnetosphere behaves like a stressed web that suddenly breaks and reknots. The brightening is not a fire in the ordinary sense. It is the rapid conversion of field structure into radiation and motion. If we could slow time down, we would see arcs collapsing, reconnecting, and flinging particles along new paths. Crustal yielding is central because it sets the trigger threshold, the point where the system cannot hold its shape. The crust can store elastic energy and magnetic stress until a yield point, which depends on composition, temperature, and defects. When it yields, the change is sudden, and the magnetosphere is forced to respond. The quake is not just a crack, but a rearrangement of anchoring points for magnetic flux. Accessible scaling keeps this from becoming abstract, because numbers can anchor intuition. Magnetic pressure scales as b² over 8 pi, so doubling the field quadruples the pressure. For b near 10 to the 15 Gauss, magnetic pressure is so large that terrestrial material strength becomes irrelevant. It is pressure that does not need contact because it is carried by the field itself. Compare it to steel, because steel is a human reference for strength and failure. The yield strength of steel is around 1 billion pascals depending on alloy and treatment, and that already feels immense. Magnetic pressure near a magnetar can exceed that by many orders of magnitude, which is why the crust is always living near failure. The surprising part is not that it breaks, but that it holds at all. To picture pressure, imagine a force that would crush mountains into powder, then keep going. The crust is not resisting with chemical bonds like rock does. It is resisting with a lattice of nuclei embedded in a sea of degenerate electrons, under gravity that pins everything down. That gravity is so strong that the surface is effectively locked in place, even while it strains. The crust survives only because it is not steel and not rock, and because it is supported by extreme density and pressure. It is a dense Coulomb lattice under immense compression, with a shear modulus far beyond Earth materials, and it is threaded by magnetic flux. Even so, the field can win, and the crust can hold stress only until it fails catastrophically. When it fails, the release can be localized, but the consequences can be global. This is the mechanical heart of the monster, and it explains the long, quiet periods between outbursts. The magnetar is a solid shell over a super-dense interior, with a magnetic field trying to untwist and relax. The shell delays the release, which allows energy to build, and delay is what makes the eventual release violent. Quiet is not peace here, it is loading. Now bring timing into the same framework, because timing is how we listen to a star we cannot approach. Magnetars are pulsars, so their rotation stamps a period onto their emission, often between seconds and tens of seconds. But their timing is noisy, and that noise is information about stress and coupling. A clean clock would be comforting, but magnetars rarely offer comfort. A stable pulsar is a metronome, and that stability is why pulsars were once proposed as cosmic clocks. Magnetars are different. Their pulse arrival times wander, and their spin-down rate can change, as if the clock is being tugged by invisible hands. Sometimes the tug is gradual, and sometimes it is a sudden jerk. Glitches are sudden spin-ups, often interpreted as angular momentum transfer from a faster superfluid interior to the crust. In magnetars, glitches can coincide with bursts, suggesting that internal rearrangements and magnetospheric events are linked. The star can change its rotation and its radiative state in the same episode. That coincidence is a clue that the interior and exterior are not separate stories. The superfluid picture is strange but well motivated, because neutrons at these densities can pair and flow without viscosity. That superfluid stores angular momentum in quantized vortices, tiny whirlpools that can pin to the crustal lattice. When many vortices unpin, the crust can jump forward in rotation. It is a microscopic mechanism with a macroscopic signature, written into pulse arrival times. Anti-glitches are rarer and more unsettling, because they are sudden spin-downs that defy the usual glitch story. They suggest either a sudden increase in external torque, or an internal event that effectively slows the crust relative to the interior. In magnetars, a magnetospheric twist can increase particle outflow and braking, producing an apparent anti-glitch. The same kind of twist that brightens the star can also slow it. An anti-glitch is a clue that the magnetosphere is not merely a passive halo. It can reach back and change the star's rotation by changing how efficiently angular momentum is carried away. In that sense, magnetars blur the boundary between interior physics and space weather. The star's spin becomes a record of its own magnetic storms. Timing noise is the background weather of the system, and it can be persistent even in quiescence. Pulse arrival times wander beyond simple spin-down models, and the wander is not random in a trivial way. That wandering can reflect changing magnetospheric currents, changing open field line regions, and intermittent particle winds. Over months, the timing can look like a coastline jagged with hidden structure. These timing behaviors also speak to the interior, because the crust is not always perfectly locked to the core. Neutron star interiors likely contain superfluid neutrons and superconducting protons, and those phases can interact with magnetic flux. Vortices and flux tubes can pin and unpin, changing how the crust couples to the core. The coupling is a kind of frictionless clutch, and it can slip. When coupling changes, the crust can temporarily decouple from the interior, like a shell slipping on a core. The observed rotation then reflects only part of the star, until angular momentum is exchanged again. Glitches become a probe of superfluid dynamics, and magnetars add magnetic stress as an extra driver. The same dataset can therefore contain both magnetic and fluid information intertwined. The same timing data also constrain magnetospheric geometry, because torque is set by the field's open structure. If torque changes without a corresponding change in thermal emission, that hints at a magnetospheric reconfiguration rather than deep heating. If torque changes with spectral hardening, that supports the twisted magnetosphere picture. The star tells us, indirectly, where the change occurred. Now return to the measurable outputs that keep the physics grounded, because each measurement is a handle on an unseen machine. Spectra tell us temperatures, scattering, and non-thermal tails that hint at particle acceleration. Pulse profiles tell us geometry, hotspot sizes, and beaming patterns shaped by magnetic opacity. Even small changes become meaningful when they repeat across sources and across years. Polarization tells us whether vacuum birefringence is real in the sky, and whether the vacuum is acting like a medium. It also tells us whether photons are being processed by magnetospheric currents rather than leaving directly from the surface. Timing tells us whether the star is stable, or whether it is actively rearranging its interior and magnetosphere. Together, these measurements act like different senses, each sensitive to a different layer. These are the handles we have on an object we cannot touch, and they are surprisingly powerful. We cannot sample a magnetar crust, but we can watch its light change after a burst and track the relaxation. We cannot see the twist directly, but we can infer it from torque, hardness, and phase-resolved spectra. The detective work is slow, but the clues are consistent. There is also a broader historical arc to this detective work, because magnetars were not immediately recognized. Soft gamma repeaters and anomalous X-ray pulsars were once separate mysteries, named for what they did rather than what they were. The magnetar model unified them by making the magnetic field the central energy source. That shift changed the questions scientists asked, and it changed what they looked for in the data. That unification matters because it makes predictions that can be checked, and checked repeatedly. A higher inferred field should correlate with stronger persistent X-ray emission, more bursting activity, and stronger timing irregularities. The correlations are imperfect, but the pattern is there, and it guides how we interpret new sources. Imperfection is expected because geometry and viewing angle can hide or exaggerate what is happening. The deeper implication ties back to the central question about lethality, because the same physics that shapes a spectrum also shapes a hazard radius. A magnetar's field can convert stored stress into radiation with very high efficiency, and it can do so abruptly. The conversion is not limited by fuel supply because the reservoir is the field itself. The star does not need to burn anything to flare, it only needs to rearrange. When the field reconfigures, the output can be hard X-rays and gamma rays that cross the galaxy and still matter. The spectrum matters for atmospheric chemistry because harder photons ionize efficiently and penetrate deeper before being absorbed. The beaming matters for kill radius because a narrow beam turns distance into a weaker shield. A planet's fate can depend on whether it sits inside that beam for a few seconds. A thought worth holding is that the magnetosphere is not just a place where light passes through. It is a machine that shapes the light into something more damaging or less, depending on how it scatters and splits photons. The hazard is not only energy, but the way that energy is packaged. In cosmic disasters, packaging is often the difference between a scare and a collapse. So the physics of twist and QED is not academic, even if it sounds like it belongs in a theory seminar. It shapes the burst spectrum and the angular pattern of your mission, and those control what reaches a planet. It determines whether a flare is a broad flash or a concentrated pulse that can reach farther with the same energy. The most dangerous event is not necessarily the most energetic one, but the one best aimed and best tuned. We also need to be clear about what magnetars cannot do, because clarity is part of mystery. They do not need to throw debris to be lethal, and they do not need to be nearby in an astronomical sense. Their danger is that photons are fast, and the atmosphere is vulnerable to ionization cascades. The damage can be silent, global, and invisible until biology feels it. A magnetar can be thousands of light years away and still matter if the flare is strong and the beam is aimed. That is an uncomfortable idea because it means distance is not always safety. It also means the sky contains hazards that leave no crater, only chemistry. If a civilization disappeared without impact scars, what would we assume happened? The magnetosphere is therefore the firing chamber, and its geometry is the safety and the trigger. Closed field lines store and trap. Open lines drain and break, and the boundary between them can shift. Twists load the chamber with currents and energy, and reconnection can release it abruptly. The same structure that makes a magnetar bright also makes it unpredictable. The crust is the safety catch that sometimes fails, and failure is not gentle. It holds stress, it yields, and it launches waves into the magnetosphere, which then answers with radiation. When it yields, the magnetosphere can respond faster than any mechanical process on Earth. In that speed is the signature of a system dominated by fields rather than friction. This chapter has built the chain from field strength to observable signatures, so the monster has a measurable outline. It has also shown why magnetars exceed a threshold where vacuum and matter behave differently, and why that difference is predictable. That difference is not mystical. It is physics with consequences that instruments can test. The closer we look, the more the universe resembles a laboratory, though the apparatus is lethal. Now the narrative has to pivot from stress to rupture, because stored energy is only half the story. We have described how energy is stored in twisted fields and strained crust, and how that storage shows up in spectra and timing. The next step is the moment the storage fails, and the star speaks in a burst that can cross interstellar space. The question is not whether it can happen, but what the failure looks like in detail. A magnetar flare is not only a flash, it is a reconfiguration event, like a sudden change in the star's magnetic architecture. It is the system dropping to a lower energy state and shedding the difference as radiation and particle outflow. The question is what triggers the drop and what the drop looks like in real data. Every flare is a clue to the hidden threshold that was crossed. In observations, that drop can have a sharp spike, a pulsating tail, and a long afterglow, each phase tied to different physics. The spike suggests rapid reconnection and pair fireball formation near the star. The tail suggests trapped plasma cooling, while the star's rotation modulates what we see. The afterglow suggests a crust and magnetosphere that are still rearranging, long after the initial fracture. From here, we move from the slow build of stress to the fast mechanics of failure, where milliseconds matter. We move from magnetospheric weather to magnetospheric lightning, where the sky can change before a human breath finishes. We move toward the Starquake, where the monster finally makes sound in the only language space carries, which is light. Magnetars become infamous in the moments they stop being steady sources and become events, because a quiet X-ray glow is easy to ignore. Their danger is not mass or gravity acting at distance, and it is not a slow tidal influence that gives you time. Their danger is a brief, hard pulse that turns magnetic stress into gamma radiation, and it does so with the indifference of physics. A magnetar can sit in the sky like a cold ember, barely brighter than background in a casual survey. Then, without warning, the ember becomes a camera flash of high-energy light, bright enough to rewrite chemistry on worlds that never knew it existed. That contrast is part of the mystery, because the same object can be both persistent and explosive, depending on how its field is arranged. We are watching a machine whose fuel is not matter falling in, but magnetic structure trying to simplify itself. Chapter 1 described the kill mechanism as atmospheric chemistry rewritten by high-energy photons, where ionization cascades manufacture nitrogen oxides and shred ozone faster than it can recover. Chapter 2 built the magnetic reservoir that can pay for that rewrite, showing how a neutron star's field can store energy like a wound spring. Chapter 3 mapped the magnetosphere as the firing chamber where twists, currents and pairs shape emission, and where a small change can propagate at near light speed. Now we focus on the signature failures that made magnetars a category in the first place. Observers learned to sort magnetar outbursts by duration, fluence and structure, because those simple measurements are fingerprints of deeper processes. Duration hints at how long the energy release can be sustained, while fluence measures the total dose delivered to space. Structure, spikes, bumps, tails, and pulses reveals how the magnetosphere rearranges itself while we watch. Even when detectors saturate, timing still survives, and timing is often the first clue. The smallest are short bursts that last milliseconds to seconds, often clustered in storms that look like popcorn in a light curve. They repeat from the same source, which is why early catalogues called them soft gamma repeaters, even before the word magnetar felt inevitable. Their spectra are hard compared with thermal X-rays, yet softer than classical gamma-ray bursts, sitting in an in-between regime that hinted at an exotic engine. That soft label is relative. These are still photons energetic enough to ionize air and strip electrons from atoms. Short bursts are common enough to be routine for active sources, which is exactly why they became the training data for magnetar behavior. They rise fast, often within a few milliseconds, then decay in tens to hundreds of milliseconds as the emitting plasma cools and thins. Many show spectral evolution as the scattering depth changes, so the same burst can harden and soften in a recognizable arc. The rise time is a clue about causality, because nothing larger than a few hundred kilometers can coordinate itself in a millisecond. Their energies vary widely, but the key point is their frequency and unpredictability, because the star can flicker without warning. Some bursts are so short that a single time bin contains most of the energy, leaving a needle that looks almost artificial. Others have faint precursors, like a match struck before the flare, suggesting the system tests a threshold before it crosses. When storms happen, the repetition feels like a fault line slipping in a series of jerks, each one relieving stress and then reloading nearby regions. When you visualize them, the scene is almost clinical: a flat baseline, then a needle-like spike, then a ragged tail that falls back into quiet. In some storms, dozens of spikes arrive within minutes, separated by seconds that feel like held breath. The magnetar is not exploding once, but repeatedly snapping at its own magnetic restraints. Even when each burst is modest, the repetition tells you the system is near a threshold. Intermediate flares sit between short bursts and the rare giants, and they are the category that makes the continuum obvious. They last seconds to minutes, and can release far more energy than a typical burst, sometimes by orders of magnitude. They often show a smoother envelope, sometimes with substructure that hints at multiple reconnection episodes rather than one clean release. They can also produce extended tails that look like a magnetosphere struggling to settle, as if the field is ringing after being struck. In intermediate events, the light curve can resemble a wave with ripples riding on top, and those ripples matter. Each bump can be a separate injection of energy, or a separate patch of field lines losing stability. The spectrum can also drift during the event, because the plasma density and temperature are not constant. If you want to see the coupling between crust and magnetosphere, without the overwhelming violence of a giant flare, intermediate flares are the bridge. That bridge matters historically, because intermediate flares helped convince observers that magnetars were not just odd repeaters. They showed that a single source could produce a hierarchy of failures, as if the same engine had multiple gears. The implication was uncomfortable but elegant. The star is not switching to a new mechanism each time, it is changing the scale of the same mechanism. In that sense, the taxonomy is not a filing system, but a map of how stress can break. Then there are giant flares, the events that reset the scale of what a neutron star can do, because they behave like a new class of transient. They are rare enough that only a few have been seen clearly in decades of monitoring, which is why each one became a landmark paper. Their light curves have a distinctive two-stage form that is hard to mistake when you have seen it once. First comes an initial spike that saturates detectors, then a pulsating tail that can last minutes, fading like a lighthouse behind fog. The initial spike is brutally fast and bright, and its brevity is part of its menace. It rises in milliseconds and can be over within a fraction of a second, so the peak can outrun instrument response. In that instant, the luminosity can exceed the combined output of many stars in a galaxy, at least for a heartbeat of time. The spike is the moment the magnetosphere reconfigures and dumps energy into radiation and pairs, converting field stress into photons with ruthless efficiency. What makes the spike feel uncanny is how clean it can look in time, like a single decisive snap. The physics behind it is not clean at all, because it involves plasma instabilities, current sheets, and magnetic topology changing in a volume only a few stellar radii across. Yet the light curve compresses that complexity into a sharp flash, as if the star chose a single moment to speak. For Hazard, that compression is everything, because dose delivered in a fraction of a second leaves no time for buffering. The tail is slower and structured, and it carries a different kind of information because it is not just brightness. It pulses at the Magnetar's rotation period, typically a few seconds, and those pulses persist as the tail fades. The modulation looks like a stamp pressed into a cooling fireball, repeating with metronomic insistence. The tail is why giant flares are not just bright, but diagnostic, because it lets us measure the star while it is still on fire. The pulses are also a reminder that we are not seeing a uniform sphere of light. We are seeing a mission shaped by geometry, by where field lines close, where plasma is trapped, and where opacity is highest. As the star rotates, the beam pattern sweeps past us, and the tail becomes a rotating laboratory. The same event that threatens atmospheres also reveals the Magnetar's architecture, if we listen carefully. This burst taxonomy matters for the central question about lethality, even if the labels sound like bookkeeping. A planet does not care whether we call an event a burst or a flare, because chemistry responds to dose. It cares about photon energy, total fluence, and how quickly the dose arrives, since fast ionization can overwhelm natural buffering. Taxonomy is our way of linking light curve shapes to physical triggers and hazard reach, so we can translate an observed flash into a credible radius of harm. The leading trigger model begins in the crust, where magnetic stress loads a solid lattice beyond its comfort zone and keeps loading it. Internal fields drift and twist over years to centuries, pushing against the crust's anchoring points like a slow pry bar. The crust resists through elastic strain until it reaches a yield threshold, and that threshold depends on temperature, composition, and microstructure. When it yields, the change can be sudden enough to launch waves into the magnetosphere, and sudden is the key word. A starquake is not an earthquake scaled up in a simple way, because the material and the forces are alien. The crust is roughly a kilometre thick and pinned by gravity so strong that mountains are measured in millimetres, not kilometres. It is also threaded by magnetic flux that can apply stress without contact, because the field couples regions that never touch. Failure can be brittle cracking in colder regions, or plastic flow where the lattice creeps and shears under sustained load. Both modes can release energy, but they differ in timescale and in how sharply they drive the magnetosphere. Under that crust, density climbs toward nuclear values, and the boundary between solid and fluid is not a simple line. The outer layers behave like a Coulomb crystal, where positively charged nuclei form a lattice immersed in a sea of degenerate electrons. Deeper down, nuclei become more neutron-rich, and free neutrons begin to seep through the structure like a superfluid component. These details matter because they change how stress propagates, and how quickly a disturbance can couple to the magnetic field. Elastic deformation stores energy like a spring, then releases it abruptly when the lattice fractures or slips along a weak plane. Plastic deformation bleeds stress through gradual motion, yet it can still concentrate strain into localized shear bands that fail suddenly. A magnetar can do both, sometimes in the same episode because different depths and temperatures favor different behavior. The crust can creep for months, then fail in milliseconds when a critical region gives way, and the transition can be violent. To picture the crust, imagine a dense crystalline shell under unimaginable pressure, with nuclei packed into a lattice and electrons moving like a relativistic sea. The lattice is not a rock in the everyday sense, yet it can still store elastic strain and then snap. Magnetic fields of 1014 to 1015 Gauss thread through it, so the field is not a background condition. It is an active mechanical agent, tugging at the lattice and forcing it to accommodate stresses that would be impossible on Earth. The quake does not need to open a visible fissure to matter, because the key is geometry rather than a crack you could photograph. What matters is that magnetic footpoints move, because the magnetosphere is tied to those anchors like a tent to its stakes. A small shift can change current patterns across a large volume, and those currents are what sustain twists in the external field. That shift can also excite Alfvén waves that carry energy outward along field lines at relativistic speeds. The magnetosphere receives the message almost immediately, because the signal rides the field itself. Alfvén waves are the magnetized plasma's way of transmitting stress, and in a magnetar they are almost absurdly fast. The relevant speed approaches the speed of light when magnetic energy density dominates particle inertia, which it often does near the star. So the magnetosphere does not gradually notice a quake. It is struck like a bell. The ringing can set up oscillations that modulate emission, and some observed quasi-periodic features have been discussed in that context. Once the magnetosphere is forced out of equilibrium, reconnection becomes the fast-release valve, and fast is literal. Twisted field lines can become unstable and snap into a lower energy configuration, breaking and rejoining like stressed rubber bands. Reconnection converts magnetic energy into heat, bulk motion, and particle acceleration, and it does so in a region that can be only kilometers across. In magnetars, that conversion is efficient enough to create a dense pair plasma in a fraction of a second, and the environment becomes opaque almost instantly. Pair plasma means electrons and positrons created by gamma rays in strong fields, and it is one of the reasons magnetars feel like a different astrophysical species. When photon energies and field strengths are high, pair creation becomes easy, because the field can absorb momentum and make the reaction possible. The magnetosphere can suddenly fill with charge carriers that increase opacity and scattering, changing how radiation escapes. This is how a mechanical trigger in the crust becomes a radiative catastrophe in space, and the chain has no weak link. In the giant flare picture, reconnection and pair creation form a hot fireball near the star, and near means only a few stellar radii above the surface. The fireball is trapped by closed magnetic field lines, which act like a cage that resists expansion through magnetic pressure. It radiates as it cools, but it cannot expand freely because the field confines it, forcing energy to leak out rather than blow out. The trapped fireball model explains why the tail lasts minutes instead of milliseconds, because confinement turns an explosion into a slow burn. Visually, the trapped fireball is a glowing knot of plasma suspended above a black compact star, wrapped in invisible loops of magnetic field. The star itself is only tens of kilometers wide, yet the magnetosphere extends far beyond, a volume where field energy dominates matter. During the tail, that knot shrinks and dims, but it does not vanish at once. It cools under constraint, and the constraint is the field. You can imagine the magnetic loops as luminous arcs drawn in negative space, seen only by what they force the plasma to do. The fireball presses outward, the field presses back, and the balance sets the size of the glowing region. As the pair density drops, the plasma becomes more transparent, and the light changes character. What begins as a trapped furnace becomes, minute by minute, a thinning veil. The initial spike is the part that can reach farthest with the hardest spectrum, which makes it the phase that matters most for distant damage. It is short enough that peak luminosity becomes extreme, and extreme luminosity means intense ionization per unit time. It is also hard enough that it couples efficiently to atmospheres through ionization and dissociation, driving cascades that multiply the damage. This is the phase that can turn distance into the only shield, because shielding by time is not available. Energy numbers keep the story honest, because magnetars are terrifying partly by arithmetic rather than metaphor. A major flare can release roughly 1044 to 1046 ergs in high-energy radiation, concentrated into hard X-rays and gamma rays. That range depends on distance estimates, beaming, and detector saturation, which is why papers often quote bands rather than a single number. Even the low end is enormous for an object only tens of kilometers wide, and the high end is difficult to hold in the mind. It also helps to translate the units, because ergs can feel like a private language. 1 erg is tiny, but 1046 ergs is about 1039 joules, an amount of energy that would dwarf any terrestrial scale. And unlike a supernova, which spends most of its energy on neutrinos and kinetic expansion, a magnetar flare puts a meaningful fraction directly into ionizing photons. That is why the hazard discussion keeps returning to spectrum and timescale, not just total energy. The famous line is often quoted because it compresses the scale into a human sentence, and humans need sentences. A giant flare can release more energy in 1 second than the sun emits in 100,000 years, and the comparison feels like a dare. In luminosity terms, that means about 10^38 watts multiplied by 3.1 times 10^12 seconds, landing near 10^50 ergs of energy for the sun over that span. The exact value varies with solar luminosity and rounding, but the point is that the flare's instantaneous power is absurd. That sentence can mislead if it sounds like total energy equals a star's lifetime output, because it invites the wrong picture. The sun's energy is spread over time and across a broad spectrum, with most of it in visible and infrared that warms rather than ionizes. A magnetar flare is concentrated into seconds and pushed into hard X-rays and gamma rays, which are chemically aggressive. For hazard, concentration matters more than the poetic comparison, because chemistry responds to peak ionization and integrated dose. Timescales are part of the threat because biology and technology respond differently to milliseconds and minutes, and the atmosphere responds faster than either. The initial spike can arrive faster than satellites can switch modes, so even hardened instruments can be caught in the wrong configuration. Detectors can saturate, and the true peak must be reconstructed indirectly from partial data and secondary effects. A planet's upper atmosphere, however, responds immediately because ionization is fast, and the first chemical steps begin before the tail even forms. The tail arrives on human timescales, long enough to measure structure and polarization, and long enough to watch the system evolve. It is also long enough to deliver additional dose, though typically at lower luminosity than the spike, and lower luminosity does not mean harmless. The tail's modulation is locked to rotation, which makes it a probe of geometry rather than just energy. Each pulse is a slice through the emission region as the star turns, like scanning a beam across a detector. Rotational modulation implies that the emitting plasma is not symmetric around the spin axis, because symmetry would smear the pulses away. In the trapped fireball model, emission is channeled by magnetic geometry into preferred directions, shaped by where field lines close and where opacity is highest. As the star rotates, our line of sight cuts through brighter and dimmer regions, and the pulse profile becomes a map. The pulse profile therefore encodes field topology and the location of the trapped plasma, even if we cannot resolve the star. The tail also reveals how confinement works in fields this strong, because the decay is a measurement of leakage. If confinement were weak, the fireball would expand and cool too quickly to sustain minutes of emission, and the tail would be a brief afterglow. If confinement were perfect, pulses might be sharper and more stable than observed, because the geometry would be rigid. The observed decay and evolving pulse shape suggest a cage that leaks and rearranges as it cools, with the magnetosphere gradually relaxing. There is also a subtle diagnostic in how the tail softens with time, because cooling changes the photon distribution. Early in the tail, scattering can keep photons hard, maintaining a high effective temperature. Later, as the pair density drops, the optical depth falls and radiation escapes more directly, so the spectrum softens. That evolution is not just a detail for specialists, because it tells us how quickly the magnetosphere empties itself of pairs. Spectra matter because not all photons are equally effective at damaging atmospheres, and the difference is not intuitive. Hard X-rays and gamma rays penetrate deeper before being absorbed, creating ionization cascades that spread energy through secondary electrons. Softer X-rays deposit energy higher up, altering chemistry, but with different altitude profiles that can change the net ozone response. The spectrum controls how much nitrogen oxide is produced and how ozone depletion unfolds, because the chemistry depends on where ionization happens. In magnetar flares, The spectrum is shaped by scattering and Comptonization in the pair-rich magnetosphere, which acts like a turbulent radiative filter. Thermal photons from the surface and fireball are upscattered by relativistic charges, gaining energy in repeated collisions. Multiple scatterings can build a hard tail that extends into gamma energies, even if the seed photons began as softer X-rays. The details depend on optical depth, magnetic field strength, and the distribution of particle energies, and those details can change during the flare. Pair cascades are the engine that keeps the magnetosphere opaque during the flare, and they are self-sustaining for as long as conditions allow. High-energy photons create pairs, pairs radiate and scatter, and those photons create more pairs, closing a feedback loop. The cascade can regulate the spectrum by converting extreme gamma rays into a thicker bath of lower-energy photons, a kind of radiative crowd control. This regulation can still leave a lethal output, but it changes how far the hardest photons travel, and it shapes what distant detectors see. The spectrum also determines what distant instruments classify the event as, which is where magnetars start to interfere with other fields. A giant flare seen nearby looks like a spike plus a pulsating tail, and the tail is the giveaway. The same flare seen from another galaxy may show only the initial spike, because the tail falls below detection thresholds as distance eats flux. At extragalactic distances, a Magnetar giant flare can masquerade as a short gamma-ray burst, and the disguise can be convincing. This matters for cosmology, because transient catalogues are built from what instruments can detect, and detection is never neutral. Short gamma-ray bursts are often linked to neutron star mergers, which are now confirmed by gravitational wave events and their multi-wavelength afterglows. Yet a fraction of short bursts in catalogues could be misidentified Magnetar flares from other galaxies, especially when localization is poor. That contamination changes rate estimates and complicates population studies, because it mixes two engines with different physics. The masquerade problem is not only academic, because it is a reminder that classification depends on distance and sensitivity, rather than essence. A tail as obvious in the Milky Way becomes invisible beyond a few megaparsecs, and the event collapses into a single spike. Without the tail, the light curve looks like a compact hard flash, which fits the short burst template that observers already use. The universe can hide magnetars inside other categories, and our catalogues inherit that ambiguity. Historically, this is part of why magnetars took time to become accepted as a unified idea, rather than a set of odd sources. Soft gamma repeaters were first recognized as repeaters, not as a new kind of neutron star, because repetition was the observable fact. Anomalous X-ray pulsars were recognized as pulsars with puzzling power sources, because their spin-down energy did not pay the radiative bill. The Magnetar model linked them by proposing that magnetic energy, not rotation or accretion, was the primary fuel. Giant flares then acted like decisive demonstrations because only an extreme magnetic reservoir makes them plausible. There is a quiet human story inside that acceptance, because it required instruments that could catch the sky's fastest surprises. Early gamma-ray detectors were built for other reasons, including monitoring nuclear tests, and they accidentally opened a new window on cosmic flashes. As the catalogues grew, repetition stood out as a pattern that demanded explanation, even when the sources were poorly localized. Magnetars became a category when the patterns became too coherent to dismiss. Back in our galaxy, the reach of a giant flare is not hypothetical, because we have already seen it touch Earth. A flare can be tens of thousands of light years away and still affect Earth's ionosphere, changing radio propagation and measurable electron densities. That is not a kill event, but it is a detectable handshake across the disk. It proves that the radiation couples to our atmosphere even after traveling through interstellar space, and it proves the dose is not zero. The deeper implication returns to the opening hook about a silent pulse within 1,000 light years, because distance is the variable that turns a curiosity into a catastrophe. If a giant flare occurred that close, the same physics that nudged the ionosphere could drive catastrophic ozone loss, and the timescale would be brutally short. The danger would arrive at light speed, with no warning beyond whatever our monitors happen to catch, and no way to intercept it. There would be no debris, only chemistry and aftermath, and the sky would look normal again. It raises a question that is unsettling precisely because it is practical. How many magnetars exist close enough to matter, and how many are quiet enough to be forgotten between outbursts? The Milky Way is dusty, and many neutron stars are hidden behind gas that blocks softer X-rays. A threat does not need to be common to be important if its consequences are global. To understand how a crack becomes a galaxy-scale flash, we have to keep the chain intact because breaking the chain invites magical thinking. Magnetic stress builds in the interior and crust as fields drift and twist, and the drift is slow enough to feel like stability. The crust yields through fracture or plastic flow, shifting magnetic footpoints by meters or less, yet those meters matter. That shift launches waves and triggers reconnection, which creates a pair fireball and a hard photon spike, and the spike is what escapes. The spike is the detonation, but the tail is the autopsy because it lets us measure what the blast left behind. The tail's pulses tell us the rotation period and confirm that the emission region is magnetically confined rather than freely expanding. The decay time tells us about fireball cooling and leakage, and about how quickly pair density collapses. The changing spectrum tells us about scattering depth and particle energies, which are otherwise hidden. A giant flare is therefore both a threat and a diagnostic event, and the duality is part of its scientific value. Short bursts and intermediate flares fit into the same framework at smaller scale, which is why the taxonomy feels like sizes of the same failure. A localized crustal slip can trigger a small reconnection event and a brief burst, and the magnetosphere can settle quickly afterward. A larger yielding region can drive a longer flare with extended emission, because more field lines are forced into instability. The taxonomy is not separate mechanisms, but different sizes and geometries of the same coupled failure, scaled by how much of the field is forced to change. There is also feedback, which is why magnetars can enter active phases that last months or years. A flare can rearrange the magnetosphere and change the external torque, so the star's spin-down rate can jump. It can also heat the crust and alter conductivity, which changes how stress accumulates afterward and where currents prefer to flow. After an outburst, persistent X-ray emission can rise and then decay over months as the system relaxes, like a hot metal cooling. The star can remain in a stress state that makes further bursts more likely, and the clustering becomes understandable. This feedback complicates prediction, which matters for hazard assessment because the dangerous events are rare and the warning signs are ambiguous. A magnetar does not flare on a simple schedule, and it does not count down in a way we can read. It loads stress through slow magnetic evolution, then releases it in clustered episodes, sometimes with quiet gaps that feel deceptive. The most dangerous events are rare, but they may be preceded by smaller activity that is easy to miss behind dust or instrument gaps. The question is not whether the star is capable, but whether we notice it becoming restless. For Earth, the practical variables are distance, beaming, and spectrum, because those are the knobs that set dose. Total energy sets the overall budget, but beaming can concentrate that budget into a narrow solid angle, turning a global number into a directional threat. If emission is modestly beamed, the apparent isotropic energy can be misleading, because we infer energy from what we receive. A planet inside the beam receives a much higher dose than a planet outside it, even at the same distance. In a universe of narrow beams, luck becomes a parameter. Beaming in magnetar flares is still constrained mostly by indirect arguments, which is why hazard radii come with caveats. The tail's modulation implies anisotropic emission, but anisotropy is not always tight beaming, and geometry can mimic directionality. The spike may be more directional than the tail, depending on reconnection geometry and open field regions that act like vents. Uncertainty here maps directly onto uncertainty in kill radius, because a factor of a few in beam angle becomes a factor of many in risk. Even without extreme beaming, the energy scale forces uncomfortable reach, and inverse square dilution only helps so much. At 10 Fortius Ciegs, inverse square dilution still leaves a significant fluence at kiloparsec distances, especially in the initial spike. The atmosphere does not need to absorb all of it to be altered, because chemistry is non-linear and catalytic cycles amplify. It needs enough ionization to push chemistry into a new regime where ozone destruction outruns repair, and where recovery takes years rather than days. This is why magnetars are cosmic horror made real in physical terms, because the mechanism is simple once you accept the numbers. A dead star can store energy in a field, then release it as light that behaves like a weapon, and the weapon is indifferent to targets. The weapon does not need to hit the ground, and it does not need to leave a crater. It only needs to cross the sky and interact with air, turning a protective atmosphere into a reactive medium. The scientific response is not fear, but mapping and classification. because understanding is the only lever we have. Burst taxonomy links observed light curves to physical triggers and energy scales, so we can compare events across decades and instruments. Spectral modelling links photons to pair cascades and Comptonization, which links to atmospheric impact through ionization profiles. Timing and tail modulation link emission to field geometry, which links to beaming and reach, and each link reduces uncertainty. The more we connect these pieces, the less the threat feels like a myth. As we tighten the focus, one event stands as the proof that magnetars can touch Earth from across the galaxy, and it did so in modern instrument time. In late 2004, a giant flare erupted from SGR 1806-20, about 50,000 light-years away, from a direction crowded with dust and massive stars. Its initial spike saturated instruments, and its tail pulsed with the star's rotation, leaving a clear signature. It also measurably ionized Earth's upper atmosphere despite the distance, producing effects that could be tracked in ionospheric data. That is the transition point where the documentary stops being hypothetical, because the planet itself becomes a detector. A magnetar screamed on the far side of the Milky Way, and our planet registered the shock in its ionosphere, a faint but undeniable imprint. In the next chapter, we step into that 2004 flare in detail, because it is the closest thing to a full-scale test. It is the moment a stellar corpse reached across 50,000 light-years and still touched Earth. December 27, 2004 begins as an ordinary day for Earth's space weather monitors and gamma-ray sentinels, with screens full of steady background and routine solar vigilance. Operators watch familiar plots breathe with orbital cycles, detector temperatures, and the slow drift of cosmic ray noise that never truly stops. Then a hard pulse arrives from deep in the Milky Way, and instruments react before humans do. In control rooms and data pipelines, the first sign is not awe but anomaly. Counters jump, buffers choke, and plots slam into limits. This chapter is a forensic reconstruction of the giant flare from SGR 1806-20, told through clipped light curves and atmospheric echoes. The tension is not that it was nearby, because it was not, and the source sits on the far side of our own galaxy. The tension is that it was far away, and Earth still noticed, as if the galaxy briefly leaned in and tapped the planet's upper air. The story is built from fragments, because the brightest moment damaged the very measurements meant to describe it. At first, the event looks like a problem with hardware, the kind of glitch engineers dread and scientists mistrust. Multiple spacecraft report sudden count rate spikes, then flatline data, then recovery, as though someone yanked the signal cable and plugged it back in. Telemetry streams show abrupt discontinuities, and the most dramatic traces resemble a sensor hitting a ceiling rather than a sky doing something real. The pattern repeats across missions that were never designed to work together, and that independence becomes the clue that the sky did this. The first clue is timing, because timing is harder to fake than brightness when systems fail. The leading edge rises in milliseconds, faster than many detectors can sample cleanly, and it rises almost simultaneously across spacecraft separated by thousands of kilometers. Even instruments with different clocks and different processing chains register the same sudden step, and that shared step becomes a fingerprint. The main spike lasts a fraction of a second, then drops into a long structured tail that keeps talking after the scream. In gamma-ray terms, that spike is the dangerous phase, not because it lasts long, but because it concentrates the dose into a moment. Peak flux becomes extreme even when total energy is finite, and that extremity is what overwhelms electronics. It is the part most likely to saturate detectors, distort measurement, and erase the very numbers we want most. If you could see it as light, it would be a camera flash that lasts less than a blink, yet still forces the sensor to shut its eyes. Detectors do not measure energy released directly, and they never simply read out a cosmic truth. They measure counts in time bins shaped by detector area, quantum efficiency, shielding, and the spectrum of incoming photons. A photon's chance of being recorded depends on interaction physics, including photoelectric absorption, Compton scattering, and pair production at higher energies. When the flux is too high, the instrument stops being linear, and the data becomes a record of failure modes rather than a clean light curve. Saturation has a signature, and it looks like a ceiling you can hit but cannot see. The count rate climbs until it reaches a limit set by electronics and dead time, and then the recorded light curve becomes clipped. Some instruments drop events entirely while they reset, leaving gaps that mimic astrophysical structure, which is why skepticism is the first step of reconstruction. A clipped spike can look deceptively simple, and simplicity is often the mark of a detector in trouble. Dead time is not a minor correction here, not a footnote at the end of a calibration paper. After each detected photon, the detector needs a brief recovery interval, and during that interval it is blind. At giant flare fluxes, the detector spends most of its time blind, so the true incident rate can be orders of magnitude above what is recorded. The concept is plain. If the counter is busy, the sky can keep shouting, and the instrument will still report silence. Different detector technologies fail differently, and those differences become diagnostic. Scintillators can pile up pulses until separate photons blur into one, while solid-state detectors can saturate front-end electronics and lose spectral information. Some systems also have anti-coincidence logic that vetoes events resembling charged particles, which becomes complicated when gamma rays arrive in near-continuous sheets. Anti-coincidence shields designed to reject charged particles can themselves become crude gamma ray detectors when the sky is bright enough, which is exactly what happens here. So the first job is to separate the sky from the instrument, and that separation requires humility about what the plots really show. Scientists compare which spacecraft saturated, which only partially saturated, and which saw the tail cleanly. They check housekeeping channels for signs of resets, buffer overflows, and protective modes that might masquerade as astrophysics. They use differences in detector design as a tool, not a nuisance, because each failure mode is a shadow cast by the same light. The second job is to reconstruct a timeline that no single instrument captured perfectly, like assembling a film from damaged reels. The initial spike is so bright that many gamma ray detectors saturate within the first time bins, and some record only a vertical wall. Others capture a few unsaturated samples on the rise, which are precious because they define how fast the event truly begins. The tail is long enough that more instruments stay linear and preserve structure, so the story continues in the quieter aftermath. The tail lasts minutes, and it pulses at the Magnetar's rotation period, a steady beat inside a fading glow. Those pulses are the signature that the emission is tied to a rotating object, not a one-off cosmological explosion that vanishes forever. The modulation also implies anisotropic emission shaped by magnetic geometry, as if the star is sweeping a flashlight beam through a cage of field lines. In the data, the pulses look like a lighthouse pattern carved into gamma rays, and that is as strange as it sounds. The tail is not just an afterthought, not merely the smoke after the blast. In the trapped fireball picture, it is cooling plasma confined by closed magnetic field lines, rich in electron, positron pairs and high-energy photons. At these temperatures, pairs form and annihilate rapidly, and the radiation field stays coupled to the plasma until opacity drops. The decay timescale becomes a constraint on confinement strength and pair density, because a weaker magnetic bottle would leak and fade faster. The pulses themselves carry more information than a simple period, because their shape hints at geometry. A double-peaked profile suggests multiple emitting regions or a complex field topology, while changes in pulse fraction reveal how opacity evolves as the plasma thins. Phase-resolved behavior can also hint at scattering in the magnetosphere, where photons interact with charges guided along field lines. Even when absolute brightness is uncertain, the rhythm can be measured precisely, and rhythm is physics. But the spike dominates the energy budget that matters for distant impact, and it is the spike that makes this chapter uneasy. It is the part that can be hard enough to ionize efficiently, and brief enough to deliver a high instantaneous dose. It is also the part most hidden by saturation, which forces scientists to infer what they cannot directly see. The most consequential moment is the one most likely to be missing from the record. This is where the accidental network matters, because no single mission was built for a Magnetar giant flare at galactic distances. By 2004, Earth was surrounded by spacecraft carrying gamma-ray detectors for many reasons, including solar flares, planetary magnetospheres, and cosmic transients. Some were designed to trigger on bursts, while others were meant to monitor background continuously and only later reveal surprises. Together, they formed an all-sky monitoring net without a single controlling plan, a distributed instrument assembled by history rather than design. Some detectors were pointed elsewhere, yet still recorded the event through side lobes and scattering off spacecraft structures, Some were shielded or partially occulted by the spacecraft body, which reduced saturation and preserved partial information about the spike. In a few cases, the signal arrived after passing through tanks, panels, or instrument housings, and those materials acted like crude filters. Some were in different orbits which changed background and viewing geometry, and those differences become leverage when the main channel is blinded. In visual terms, imagine a ring of observers around Earth, each with a different kind of camera and a different set of blind spots. One camera overexposes instantly, another catches only the reflection in a window, and a third records the sound of shutters failing. None is perfect, yet together they constrain what happened in the sky. The reconstruction becomes a kind of triangulation in parameter space, using flaws as measurements. The net also included spacecraft far from Earth, and distance becomes an advantage rather than a complication. The interplanetary network used timing differences between widely separated spacecraft to triangulate burst locations, relying on the finite speed of light. For fast transients, separation becomes a baseline, and baseline becomes a ruler, stretching across millions of kilometers. A wavefront that looks simultaneous near Earth becomes measurably staggered across the solar system. Arrival time differences across the network constrain direction on the sky, because the wavefront reaches each spacecraft at a slightly different moment. Even when individual light curves are clipped, the leading edge timing can still be measured, and that leading edge is sharp. Analysts cross-correlate the earliest unsaturated rise, using clock corrections and known ephemerides to align records. That timing pins the event to a region near the galactic center direction, narrowing a cosmic shout to a specific neighborhood. Localization then connects the flare to a known soft gamma repeater, SGR 1806-20, already infamous for restless activity. It sits in a crowded, dusty region associated with massive stars and heavy extinction, where optical light is swallowed and infrared struggles through. The sky there is not empty black but layered haze, with star fields thick enough to confuse even careful surveys. It is not an isolated beacon in clean space, but a compact engine buried in the Milky Way's clutter. Soft gamma repeaters have a history, and that history frames why this identification matters. In the late 20th century, repeated bursts from a few sources forced astronomers to accept that some neutron stars behave like crackling magnets, rather than steady lighthouses. Earlier, many bursts were first treated as mysterious flashes with no clear home, and only persistent repetition broke the ambiguity. The term magnetar emerged as an explanation for their power, linking bursts to magnetic fields far beyond ordinary pulsars. That magnetic field claim is not rhetorical, because the numbers are extreme even by neutron star standards. Magnetars are inferred to carry surface dipole fields around 10^14 to 10^15 Gauss, strong enough to quantize particle motion and stress the crust itself. In plain language, the field can dominate matter, guiding charges and shaping radiation in ways that feel almost like engineering. When such a field rearranges, the energy released can be comparable to centuries of solar output compressed into seconds. SGR 1806-20 is linked to a massive star cluster, and the environment matters because magnetars are born from massive stars that die young. Clusters provide a plausible birthplace, a nursery where massive progenitors form in groups and explode on short timescales. The association also hints at a recent supernova, even if the remnant is hard to see through intervening dust. The cluster also complicates distance estimates, because dust and crowding distort standard candles and confuse line-of-sight associations. Distance is not a detail in this story, and it is not merely an astronomer's bookkeeping. The inferred energy scales with distance squared, so a factor of 2 in distance becomes a factor of 4 in energy, and that is a qualitative shift. For a giant flare, that difference moves the event between extreme and unprecedented, and it changes how we talk about hazards. It also changes how we interpret the magnetar's internal budget, including how much magnetic stress must have been stored before release. In 2004, distance estimates for SGR 1806-20 carried real uncertainty, partly because the galactic plane is a difficult place to measure anything cleanly. Methods included associations with the cluster, extinction measurements along the line of sight, and radio observations of the surrounding region. Some analyses used kinematic arguments based on gas velocities, which depend on galactic rotation models that are not perfect. Different assumptions produced different kiloparsec values, and each value implied a different intrinsic violence. Extinction is not just a nuisance, because it encodes the distribution of dust and gas between us and the source. By comparing observed infrared colours to expected stellar spectra, astronomers estimate how much light is absorbed, and thus how far the cluster might be. Yet dust is patchy, and patchiness turns a single number into a range, which is why the energy remains a bracket rather than a point. Even the best maps of the galactic plane have holes, and magnetars like this one live in those holes. Scientists therefore report energy as a range, not a single clean number that would falsely imply certainty. They compute isotropic equivalent energy, then note that beaming could reduce true energy while increasing directional hazard. That distinction matters because an isotropic number is a bookkeeping convenience, while a beam is a physical geometry. The uncertainty is honest, and it matters for risk, because what is safe on average can be dangerous along a beam. Even with conservative distances, the spike was extraordinary, and the word giant stops being metaphor. The peak luminosity was high enough to rival or exceed many gamma-ray bursts for a fraction of a second. Even though the engine was inside our own galaxy, the tail carried less power, but its structure confirmed the Magnetar identity with a rotating signature that mergers do not imitate. The event sits in an uncomfortable overlap region, where a galactic object briefly mimics the brightest extragalactic explosions. To back-calculate the spike's true fluence, teams use multiple strategies, each one a workaround for instruments pushed beyond specification. They use unsaturated detectors, even if they were not optimized for that energy range, because imperfect data is better than none. They used detectors that saw the event through scattering, which effectively reduced flux, turning spacecraft walls into accidental attenuators. They also compared different time resolutions, because a coarse bin can hide a sharper peak and bias the inferred maximum. They also used the physics of detector response, because the failure modes are governed by measurable electronics. Given a measured clipped rate and known dead time, one can infer a lower bound on true incident rate, and sometimes a plausible range. Some instruments have parallelizable dead time, where each event extends the blind interval, while others behave non-parallelizably, and that distinction changes the correction. One can also model how pulse pileup distorts recorded spectra, because two photons arriving too close together can masquerade as one harder photon. Counts must be converted into energy fluence, and that conversion is where astrophysics meets calibration tables. It requires an assumed or fitted spectrum because detector efficiency depends on photon energy and interaction cross-sections. Analysts fold spectral models through response matrices, then test whether different instruments can be reconciled within uncertainties. A harder spectrum can deliver more energy per count, and it can penetrate deeper into materials and atmospheres, which is why hardness matters for biological and chemical coupling. The spike spectrum is often modelled with a hard component consistent with a hot pair plasma and Comptonized emission, where photons gain energy by scattering off energetic electrons. At the highest compactness, photons and pairs approach a quasi-thermal equilibrium, but rapid expansion and magnetic geometry can keep the spectrum non-ideal. The tail spectrum is softer and evolves as the trapped plasma cools and becomes more transparent, shifting the balance of energies over time. The spectral evolution is part of the mechanism, not a decorative detail. In Magnetar theory, the spike is linked to a sudden rearrangement of magnetic fields, like a stress structure snapping into a new configuration. The crust may fracture under magnetic stress, and the magnetosphere can reconnect, releasing energy into a compact region. Reconnection is not magic, but a plasma process where field lines change partners and dump stored energy into particles and radiation. That energy rapidly creates a dense photon, pair fireball, and the fireball's expansion and opacity shape the first fraction of a second. The tail, by contrast, is the fireball's captive phase, when it's trapped by closed field lines and leaks energy gradually. Radiation pressure, pair annihilation, and magnetic confinement negotiate the cooling curve, producing a decay that can be fit and compared to models. As the plasma thins, the photosphere recedes, and the observed spectrum tracks the retreat in energy. When the pulses ride on top of that decay, they reveal that the emitting region is not uniform but structured by the star's magnetic topology. The reconstruction also uses something outside the spacecraft, something no mission proposal listed as a primary instrument. Earth's atmosphere becomes a detector, because high-energy photons ionize the upper layers almost immediately, altering conductivity and chemistry. The planet records the event as a change in the ionosphere, a global membrane that responds to radiation like a photographic plate. It is a reminder that we live inside a detector and that the sky can write on it. The ionosphere is a thin region, but it controls radio propagation, which is why humans notice when it shifts. When ionization increases, electron density changes, and the reflection and absorption of very low-frequency radio waves shifts in measurable ways. In the D region, roughly tens of kilometers above the surface, chemistry is fast and sunlight normally dominates, but hard photons can briefly compete. That shift can be measured from the ground, using transmitters that hum continuously and receivers that log phase and amplitude with obsessive regularity. On December 27th, VLF transmitters and receivers recorded sudden disturbances, sharp enough to stand out from ordinary diurnal variation. Signal amplitudes and phases changed in ways consistent with enhanced ionization in the lower ionosphere, particularly the D region where VLF waves are absorbed and reflected. The propagation path acts like a waveguide between Earth and the ionosphere, so a small altitude change in reflection height becomes a measurable phase shift. The timing matched the flare's arrival, and the disturbance decayed as the ionosphere relaxed back toward its prior state. This is not a vague correlation, and it is not the kind of pattern you can explain away with weather. The disturbance begins essentially at light travel time from the Magnetar to Earth, which is the same moment the satellites are hit. The ionosphere responds on timescales of seconds, not hours, because ionization and recombination at those altitudes are fast chemical bookkeeping. When the photon pulse ends, electrons begin to recombine with ions, and the system slides back toward its usual balance. Satellite measurements of Earth's upper atmosphere also showed effects consistent with an impulsive ionizing event, adding a second independent witness. Different instruments track different altitudes and different proxies for electron content. From total electron content measurements to particle detectors sensitive to changes in the near-Earth environment. Some observations capture how quickly the disturbance spreads along magnetic field lines, because the ionosphere is electrically connected across regions. Together, they confirm a real atmospheric response, not a quirk of one receiver chain. The key is that the atmosphere did not care that the source was 50,000 light-years away, because physics is local at the point of impact. It responded to the photon flux that arrived at Earth, and that flux is what matters for ionization rate. That flux was small compared with a nearby catastrophe, but it was not negligible, and not negligible is the unsettling phrase. The planet registered the event the way skin registers a brief, sharp sting, even when no wound remains. This is where the documentary's central question tightens, because the mechanism is now anchored to a measurement rather than a speculation. What makes magnetars uniquely lethal on cosmic scales is not only total energy, which can be spread over time, it is the ability to deliver hard radiation in a brief pulse that couples efficiently to air, producing ionization where chemistry and biology are vulnerable. The coupling is not abstract, because it has already happened once in recorded data. The 2004 flare is a calibration point for that question, a real event with a real terrestrial signature. It is a known distance range, a known source class, and a measured atmospheric effect, all tied together by timing. It anchors the hazard discussion to something that actually happened, which is why this chapter feels less like theory and more like testimony. The evidence is not a single dramatic image, but a synchronized set of disturbances across instruments that were never meant to agree. It also clarifies what "we detected" it really means, because detection is often romanticized as a single telescope catching a perfect signal. We did not detect it because we were looking directly at SGR 180620 with one flawless instrument. We detected it because many imperfect instruments were in the right place, and because their imperfections were different enough to complement each other. In a sense, the event was too bright to be seen cleanly, so it had to be seen sideways. That is the value of nets of detectors, especially when the sky behaves outside design assumptions. A single satellite can fail or saturate, and a single ground station can miss the signal due to local noise or geometry. A distributed net turns partial failures into a complete record, because what blinds one instrument becomes a usable measurement in another. The network is not only redundancy, but diversity, and diversity is what makes inference possible. The flare also exposes a classification trap in astronomy, one that grows sharper as we look farther out. If the same event occurred in another galaxy, the tail would likely fall below detection thresholds, especially for instruments triggered by short spikes. Background, distance, and detector sensitivity would conspire to erase the pulsing aftermath, leaving only the initial flash. Observers would see only a short, hard spike, stripped of the signature that reveals a magnetar. A short, hard spike is the defining look of a short gamma ray burst in many catalogues, and catalogues shape how we think about the universe. Without a visible tail and without precise localization, a Magnetar giant flare can masquerade as a merger-driven GRB. Some localization regions are large enough to include many possible host galaxies, and that ambiguity invites the wrong story. The universe can hide one engine inside another label, and the label can mislead our statistics. This matters because rates inform risk, and risk is sensitive to rare events. If some fraction of short GRBs are actually extragalactic Magnetar flares, then Magnetar flare rates are higher than naive galactic counting suggests. It also means transient classification must remain probabilistic, because nature does not respect our bins and definitions. The question becomes not only what we saw, but what we failed to recognize. The 2000 author event therefore connects three domains, and it does so through the practical work of reconstruction. It connects Magnetar physics to instrument limitations, because saturation forced creative inference and cross-checking. It connects cosmic transients to Earth's atmosphere, because the ionosphere recorded the hit in radio waves we can measure on the ground. It also connects our catalogues to our blind spots, which is where the mystery lives. Dust hides magnetars in the galactic plane, and sensitivity hides tails at extragalactic distances, so our census is incomplete by construction. A source can be active yet invisible in optical surveys, and even X-ray monitoring can miss long, quiet intervals between bursts. What we call rare may be partly a function of what we can see, and what we can see depends on where we look and how our instruments fail. The galaxy is not obligated to announce its most dangerous objects in wavelengths we find convenient. Now return to the spike, because it is the part that carries the horror, and because it is the part that resists direct measurement. The spike's peak flux was high enough to overload detectors designed for the brightest solar flares, and solar flares are already extreme by everyday standards. Some instruments registered it as an event beyond their safe operating assumptions, a moment when the sky exceeded the engineering envelope. In the raw traces, you can almost feel the electronics flinch, yet the spike did not burn the ground or heat the oceans, and that contrast is important for understanding the hazard. The energy was delivered high in the atmosphere and in space, and most of it was absorbed before reaching the surface. High-energy photons interact with air by ejecting electrons and breaking molecular bonds, but they do not behave like heat that simply warms everything below. The planet was touched, not struck, and the difference between touch and strike is distance and geometry. That distinction is the pivot of this chapter, because it reframes what danger means in astrophysical terms. The Magnetar did not need to be nearby to be measurable, and measurability is the first rung on the ladder of consequence. It only needed to be powerful enough and aimed in our direction for a few tenths of a second, and that is not a comforting requirement. A brief alignment can matter more than a long, diffuse glow. Earlier chapters framed the kill mechanism as chemistry, a chain reaction in the atmosphere that begins with ionization and ends with biological stress. The 2004 flare shows the first step of that chain in miniature, with measurable ionization and radio effects that fade without catastrophe. It is a small-scale rehearsal for a closer event, a demonstration that the coupling is real. The atmosphere behaved exactly like a system that can be pushed, even if this push was gentle. The data also reinforces the physical model of giant flares, because the light curve matches the expected phases. A sharp spike suggests rapid reconnection and pair fireball formation near the star, where magnetic energy is converted to radiation in a compact region. A pulsating tail suggests trapped plasma cooling under magnetic confinement, leaking energy as the star rotates beneath its own magnetic architecture. The match is not perfect, but it is close enough to make the model feel less like a sketch and more like a map. The tail pulses also let scientists measure the rotation period precisely during the aftermath, even when other channels are saturated or noisy. That timing confirms the Magnetar's identity and links the flare to the star's persistent behavior, which is monitored in quieter times. Period stability and pulse morphology become a bridge between the extraordinary and the routine, tying the flare to the same object seen in everyday X-ray monitoring. The flare is not a separate object, but an extreme state of the same system. Like a storm that reveals the structure of the atmosphere, The forensic approach also reveals what we still do not know, and those unknowns are not trivial. Beaming remains uncertain, and beaming controls who gets hit because a narrow beam can make a rare event more locally intense. Distance remains uncertain, and distance controls how extreme the intrinsic energy must be, which affects how we model magnetar interiors and magnetic stresses. Even the spectrum is partly inferred, because saturation distorts the highest flux moments where the hardest photons may dominate. Scientists fit models constrained by what survived, then test consistency across instruments and atmospheric effects, looking for contradictions. They ask whether the inferred fluence can plausibly produce the observed ionospheric disturbance, given known ionization efficiencies and atmospheric profiles. They also check whether different detectors with different energy responses can be made to agree on a common spectral shape within uncertainties. The result is a range of plausible intrinsic outputs, bounded by physics and by the stubborn limits of electronics. This uncertainty is not weakness, and it is not a failure of modern astronomy. It is the honest boundary between measurement and inference, and it guides what new instruments should prioritize when the next rare event arrives. Better dynamic range and faster timing reduce the need for reconstruction, and they turn saturation from a wall into a manageable correction. The flare becomes a design requirement written in hindsight, a reminder that nature does not read specification sheets. The 2004 flare also changed how people think about magnetars as hazards, because it made the discussion concrete. It provided a real demonstration that a magnetar can affect Earth across the galaxy, not in theory but in recorded ionospheric data. It replaced hypothetical reach with measured coupling, and that shift is why this chapter feels like a hinge in the narrative. After 2004, the question is no longer whether magnetars can reach us, but how close they must be to matter seriously. It also reframed the opening hook, because it undermines a common intuition that distance is always safety. If a flare this far away could move Earth's ionosphere, then distance alone is not comfort, only mitigation. The question becomes how close is close enough for chemistry to fail at scale, and how often the galaxy rolls those dice. We live in a system where rare alignments can still have measurable consequences. Now we transition from detection to consequence, because the reconstruction is not the end of the story. The 2004 event tells us what a distant flare does to the upper atmosphere, a measurable perturbation that fades back into routine. The next step is to scale that effect inward, toward the kill radius, where the same physics becomes a different outcome. The math is simple, but the implications are not. Scaling is brutal because of inverse square geometry, and inverse square laws are indifferent to human intuition. Move the same event from 50,000 light-years to 5,000, and flux rises by a factor of 100, turning a disturbance into a serious chemical push. Move it to 1,000, and the factor becomes 2,500, and the word rehearsal stops being appropriate. What was a subtle ionospheric twitch becomes a forceful injection of ionization into the atmospheric system. At those distances, the ionospheric disturbance becomes the beginning of a larger chemical cascade, not a transient radio anomaly. Nitrogen and oxygen dissociation becomes widespread, and catalytic ozone loss can outrun natural repair, especially if the pulse is hard and the atmosphere is driven far from equilibrium. The key is that catalysts like NOx can persist long after the light is gone, extending damage in time even when the trigger was brief. The mechanism from Chapter 1 stops being theoretical, because the first step is already demonstrated by 2004. The 2004 flare therefore serves as a benchmark, a fixed point in a story that otherwise risks drifting into speculation. It tells us what a giant flare looks like in instruments, including how instruments fail under extreme flux. It tells us what it looks like in Earth's atmosphere, including how quickly the ionosphere responds to hard radiation. It also tells us that our planet is embedded in an active galaxy, not isolated in a quiet void. The Milky Way is not only stars and dust, but compact remnants with stored energy and unstable magnetic fields. It contains objects that can sit quietly for years, then release a concentrated pulse that crosses the galaxy in silence. When one of those remnants releases that energy in our direction, the effects propagate across space with no regard for borders, calendars, or species. The sky is not hostile in a human sense, but it is indifferent, and indifference can be dangerous. Cosmic horror here is not metaphor, and it is not a stylistic flourish. It is the measurable fact that the Milky Way contains objects that can weaponize light, and that light can reach us in a fraction of a second. The only reason this event was not worse is distance, and distance is not a guarantee, only a current circumstance. The flare is a reminder that catastrophe can be delivered as information, carried by photons that arrive already finished with their journey. The chapter ends with a question that is no longer abstract, because it is now tied to a recorded disturbance on Earth. If Earth can feel a magnetar from 50,000 light-years away, what happens when the next one is closer, and closer by an order of magnitude? And how many closer ones are still hidden in dust, waiting between outbursts, silent until they are suddenly not? The discomfort is not that the galaxy is violent, but that it can be violent without warning. We move from we felt it to what if it were closer, and that shift is the engine of the next chapter. We move from a recorded disturbance to a calculated kill radius, where the same spike becomes a chemical assault. We move from a warning shot across the galaxy to the mechanisms that could end a biosphere silently, without impact crater or fireball, only altered air and time. The fear in the hook is not impact, heat, or gravity. It is a pulse of hard light that arrives already too late. In space, light is not just illumination. At high energies, it becomes a projectile stream, carrying momentum and ionizing power. The sky does not need to change color for the chemistry of a planet to begin changing. A magnetar does not need to come near a planet to harm it. It only needs to dump magnetic energy into gamma rays and X-rays. These are photons with energies thousands to millions of times higher than visible light, and they behave less like warmth and more like a molecular hammer. The magnetar's magnetic field, so strong it can twist crustal rock, stores energy like a wound spring, and a sudden rearrangement can release it in an instant. The central question tightens here. What makes magnetars uniquely lethal is that their radiation couples to air, then air becomes the weapon. The atmosphere is not merely a shield. Under the wrong spectrum, it becomes a chemical reactor, and the products of that reactor can persist. A planet can survive a flash, yet still lose the invisible filter that makes its surface habitable. Start with the first pathway. Prompt irradiation from the initial spike delivers the highest peak flux in fractions of a second. In a giant flare, that spike can be so intense that instruments saturate, and even distant detectors register a sudden hard-edged wall of counts. Visually, you would not see a fireball in the sky. You would see nothing, while the upper atmosphere silently absorbs a blow. If we could render it, the hit would look like a thin shell of air lighting up in false color. High above the clouds, molecules would flash into ions and fragments, then settle into new chemistry. The planet's surface would remain calm, oceans unbroken, forests still, while the real event unfolds in a layer too high to hear. Even the aurora would not announce it in time, because the first assault is photons, not charged particles. That spike is short enough to defeat buffering. Biology cannot react, and technology cannot reconfigure before the dose is delivered. Cells cannot upregulate repair enzymes in a tenth of a second, and power systems cannot reroute load before the ionosphere shifts. The spike is the moment the dice are thrown. After that, the chemistry runs on its own. The second pathway is the tail and afterglow. They are dimmer than the spike, yet they extend ionization and heating for minutes to hours. That tail is often softer, with more X-rays than gamma rays, and it can keep pumping energy into the same atmospheric layers that control ozone. If the spike is a hammer strike, the tail is the grinding pressure that follows. The difference matters because chemistry integrates dose over time. A brief spike can trigger the cascade and a long tail can deepen it. Some reactions saturate quickly, while others depend on sustained production of reactive fragments, and the tail can keep replenishing them. In the language of atmospheric science, the flare is a forcing function, and the atmosphere responds with a delayed, non-linear outcome. High-energy photons matter because they do not behave like sunlight. They ionize, dissociate, and launch secondary electrons that multiply reactions. Visible light mostly excites molecules and warm surfaces. Gamma rays and hard X-rays can rip electrons free and leave behind ions that behave differently. Each primary photon can produce a small storm of secondary particles, and those secondaries are where much of the chemistry begins. In the upper atmosphere, gamma rays and hard X-rays interact through Compton's scattering and pair production. Energy is transferred into fast electrons that keep colliding. In Compton scattering, a photon strikes an electron and ricochets, losing energy while the electron shoots forward. In pair production, a very energetic photon becomes an electron and a positron near a nucleus. Both processes seed cascades, and cascades are efficient at spreading damage across altitude. Those cascades are not abstract. Picture a descending spray of electrons, each one kicking loose more electrons, like a branching lightning tree inverted into the air. The energy is redistributed into many smaller blows, and that multiplication is why a brief flash can have an outsized chemical footprint. In a simulation, you would see the deposition pattern bloom outward, an invisible bruise spreading through the stratosphere. Those electrons tear apart nitrogen and oxygen molecules. The fragments become reactive species that do not exist in large amounts normally. Molecular nitrogen is stable because its triple bond is strong, and oxygen is stable because it prefers to remain paired, yet energetic electrons do not care about stability. They punch through bonds, leaving behind atoms and radicals that immediately seek new partners. The key product is nitrogen oxides in the stratosphere. NO and NO2 are catalysts that can destroy ozone repeatedly without being consumed. They are part of what atmospheric chemists call odd nitrogen, or NOx, and they matter because they are mobile and persistent at the altitudes where ozone does its work. A flare does not need to remove ozone directly. It only needs to inject the right catalysts into the right layer. There is a reason this pathway feels familiar. The modern understanding of catalytic ozone loss was forged in the late 20th century, when measurements and theory converged on a hard lesson about trace compounds. That history matters here, because it proved that tiny concentrations placed in the right stratospheric chemistry can have planetary consequences. The ozone hole era taught us that the atmosphere can fail quietly, with no sound and little drama, until the numbers are undeniable. The mechanism is simple and ruthless. Ionization creates odd nitrogen cycles through reactions, and ozone is converted to ordinary oxygen. The basic chain is well known from decades of ozone research, including the era when chlorofluorocarbons revealed how fragile the ozone layer can be. The difference here is the trigger, an astrophysical flash rather than industrial chemistry. Ozone loss is not a single reaction. It is a catalytic chain where one NO molecule can remove many ozone molecules before it is removed. In one common cycle, NO reacts with ozone to form NO2 and O2. Then NO2 reacts with atomic oxygen to regenerate NO, freeing the catalyst to repeat. The ozone molecules are consumed, while the catalyst survives, an efficiency that turns a modest injection into a large effect. And ozone is not evenly distributed. It forms and persists in a band of altitude where sunlight, oxygen, and temperature align, creating a fragile balance between creation and destruction. When that balance is pushed, the system can slide, quietly at first, into a state where loss outruns repair. Even small shifts in temperature and circulation can tilt the equilibrium, and a flare adds a sudden chemical shove. Altitude matters because ozone is a shield only when it sits high. If NOx is produced where ozone lives, the destruction is efficient. The stratosphere is thin, cold, and sunlit, a place where photochemistry rules, and where small changes in composition can have large radiative consequences. Produce NOx too high, and it may be lost. Produce it too low, and it may be rained out. But in the ozone layer it lingers. The spectrum controls where energy is deposited. Harder photons penetrate deeper and spread ionization into lower layers, changing the chemistry profile. Softer X-rays are absorbed higher, while higher energy gamma rays can drive secondaries that reach down into denser air. That vertical profile matters because transport and removal processes differ with altitude, and so does the timescale of recovery. A softer spectrum can still be dangerous if it concentrates ionization in the ozone layer. A harder spectrum can extend damage into regions that recover slowly. In some regimes, deeper ionization can seed odd nitrogen that is less easily removed, because it sits in circulation patterns that isolate it from rapid washout. The same total energy can therefore produce different outcomes, depending on how it is distributed in altitude. Timescales follow the chemistry rather than the flash. Ionization happens in seconds, NOx builds quickly, and ozone depletion can unfold over days. The atmosphere has inertia, not in motion but in composition, and the sunlight-driven reactions that rebuild ozone do not instantly compensate. A planet can look unchanged on day 1, then slide into a new ultraviolet regime by day 10. Recovery is slower than destruction. Ozone reforms through photochemical production, and that production can be outpaced for months or years. The stratosphere must rebuild not only ozone, but also the balance of radicals that regulate it. and that balance depends on season, latitude, and circulation. A single event can therefore imprint itself differently across hemispheres, one side recovering while the other remains depleted. The strongest scenarios push the system into a long tail of harm. Knocks can persist, circulate, and keep suppressing ozone long after the sky's quiet. Stratospheric winds and the Brewer, Dobson circulation can transport these compounds, spreading depletion away from the initial deposition region. The planet's atmosphere becomes a mixing chamber, and the flare's signature becomes global. The surface consequence is not gamma rays reaching the ground. The surface consequence is ultraviolet B that was previously filtered now arriving daily. Ozone is especially effective at absorbing UVB, and even a partial reduction can raise biologically active doses substantially. The danger is not a one-time flash. It is a new baseline, a harsher sun that returns every morning. Imagine the visuals on day 12. The sunrise looks ordinary, yet instruments would show a swollen UV curve, brighter in the bands that biology fears. Shadows would still fall the same way, but the light inside them would carry a different ratio of wavelengths, an invisible shift with visible consequences. A decimeter on a windowsill would tick higher than it did last month, and no one would feel it happening. UVB is biologically efficient damage. It breaks DNA, disrupts photosynthesis, and stresses organisms that evolved under a stable ozone shield. DNA absorbs strongly in the ultraviolet, and the resulting lesions, like thymine dimers, can block replication unless repaired. Many organisms do have repair pathways, yet those pathways have limits, and chronic exposure can overwhelm them. The first ecological shock is at the base of food webs. Phytoplankton and surface ocean microbes take the UV hit with little shelter. In clear water, UV penetrates meters, sometimes tens of meters, and the organisms that live near the surface do so because light is abundant there. They're efficient at harvesting photons for energy, yet that same exposure makes them vulnerable when the spectrum shifts. Plankton collapse is not guaranteed, yet it is plausible under severe ozone loss. A small reduction in primary productivity can cascade into global shortages. If phytoplankton photosynthesis drops, less carbon is fixed, less oxygen is produced locally, and less food is available for zooplankton and fish larvae. The ocean is vast, but its productivity is concentrated in thin, sunlit layers, so a change in ultraviolet can punch above its apparent size. On land, plants face chronic UV stress during the recovery period. Growth slows, yields drop, and ecosystems lose resilience against other stressors. Some plants produce protective pigments and thicker cuticles, yet those defenses cost energy that would otherwise go to growth or reproduction. In a world already balancing droughts, pests, and nutrient limits, UV stress becomes another weight on the system. Mutation rates rise under elevated UV exposure. That can accelerate adaptation in some niches, yet it also increases developmental failure and disease burden. Evolution can respond, but it responds on generational timescales, and many long-lived species cannot pivot quickly. What looks like more variation at the genetic level can translate into fewer viable offspring at the population level. Ecological collapse is not a single moment. It is a drawn-out failure of productivity, reproduction, and stability across seasons and generations. The first year may show subtle declines, the second year may show recruitment failure, and the third year may reveal missing cohorts that never return. When the base of the food web weakens, predators starve later, and the lag can hide the cause. Now add the secondary radiation pathway. High-energy photons also create air showers, where cascades of particles propagate downward. These showers are familiar in cosmic ray physics, where detectors on mountaintops and in deserts register the footprints of particles born high above. A magnetar flare can briefly turn the atmosphere into a detector volume, filled with transient tracks of ionization. Most primaries are absorbed high, but secondaries can reach lower altitudes. Muons and other particles can increase ground-level radiation temporarily. Muons are penetrating because they are heavy cousins of electrons, and they can pass through hundreds of meters of air and even some rock. For a short time, the background radiation field at the surface can rise, not as a lingering contamination, but as a passing storm of particles. This is not a clean nuclear-style fallout. It is a brief global enhancement of ionizing radiation driven by atmospheric particle physics. There is no ash to sweep away and no plume to track, only a statistical shift in dose rates that depends on altitude and latitude. The planet is bathed, then the bath ends, leaving chemistry and biology to deal with what was triggered. The magnitude is uncertain because it depends on spectrum and angle. Harder photons and higher energies produce deeper, more penetrating showers. A flare rich in very high-energy gamma rays can seed more energetic secondaries, while a softer flare may deposit most of its energy higher. Even the angle of incidence matters, because a slant path through the atmosphere gives particles more air to traverse and more chances to dissipate. Aviation sits in the vulnerable layer. Aircraft already operate in thinner shielding, and crew and passengers could receive elevated doses. At cruising altitude, there is less atmosphere above to absorb secondaries, and the baseline cosmic ray dose is already higher than at sea level. A magnetar-driven enhancement could add a short, sharp increment, small in absolute terms for some scenarios, yet meaningful for frequent flyers and crew. Satellites are hit first and hardest. A magnetar flare can saturate detectors, upset electronics, and degrade solar panels through radiation damage. High-energy photons can induce single-event upsets in microelectronics, flipping bits and corrupting memory, while cumulative exposure can darken solar cell materials. In the worst moments, spacecraft may enter safe mode automatically, if they have time and if their sensors are not blinded. The ionosphere responds immediately, as 2004 already proved at a safe distance. Increased ionization changes radio propagation and navigation reliability. When the giant flare from SGR 1806-20 arrived, it perturbed Earth's ionosphere despite originating tens of thousands of light-years away, a reminder that far is not always harmless. The ionosphere is a thin shell, yet it is electrically active, and it reacts quickly when its ionization balance is disturbed. Communications can fail without any physical debris. HF links fade, GPS accuracy degrades, and timing systems lose integrity when ionospheric delays shift. Radio waves refract and reflect depending on electron density, and sudden changes can turn reliable paths into dead zones. Modern networks often hide this dependency, yet the dependency remains. Many systems assume that the ionosphere will behave within known bounds. Power grids add a second vulnerability layer. Ionization changes conductivity and can couple into geomagnetic systems, though the details differ from solar storms. Solar storms drive currents through geomagnetic induction, while a magnetar flare's primary influence is radiative and ionospheric. Yet both can stress long conductors and transformers. The key is not identical physics, but shared fragility. Large systems are sensitive to electrical environment changes. The key point is systemic fragility. Modern infrastructure depends on satellites, timing, and long conductors that assume a stable space environment. Even small timing errors can cascade through financial systems and data networks, and satellite outages can degrade weather forecasting and emergency response. A magnetar event would not need to destroy hardware permanently to impose global disruption. It would only need to push systems outside their design envelope. A magnetar event would be a space weather disaster with no warning from the sun. It would arrive from a random direction at light speed. We are accustomed to watching the sun for flares and coronal mass ejections, and we have built a culture of solar alerts. A magnetar flare would ignore that culture because it is not local weather, it is an interstellar lightning strike. Distance sets the basic scaling. Fluence falls with inverse square, so doubling distance quarters the dose, and halving distance quadruples it. This is geometry, not speculation, and it is why the same class of event can be a curiosity at one distance and a catastrophe at another. The radiation spreads across an expanding sphere, and a planet intercepts only a tiny patch of that sphere. That scaling makes the 1,000 light-year line useful but misleading. It is a scenario threshold, not a hard boundary between safe and dead. A planet at 900 light-years is not doomed by definition, and a planet at 1,100 light-years is not guaranteed safety. The atmosphere responds to dose and spectrum, and dose is a continuum, not a switch. Real risk depends on flare energy, spectrum, and duration. A weaker flare closer can match a stronger flare farther, and chemistry responds to dose. The integrated energy in the spike and tail both matter, and so does the hardness that sets where that energy lands. Even the season can matter, because sunlight drives the reactions that both destroy and rebuild ozone. Beaming complicates everything. If emission is anisotropic, a narrow solid angle concentrates energy, and a planet in the beam gets the full punishment. In magnetars, magnetic field geometry can channel radiation along certain directions, and reconnection can open pathways that are not symmetrical. The universe is not obligated to distribute danger evenly. The spike may be more directional than the tail, depending on reconnection geometry and open field channels. That uncertainty maps directly onto kill radius. If the spike is narrowly beamed, then most planets are spared while a few are hit hard. If it is broad, the hazard zone expands. Our models are improving, yet the data are sparse, and the rarest events are the hardest to characterize. Beaming also distorts our catalogues. We infer isotropic energy from what we receive, yet the true energy could be lower with a narrower beam. A flare that looks impossibly powerful may simply be aimed at us, while others of similar intrinsic strength may go unnoticed because they are aimed elsewhere. This selection effect is a quiet bias in every estimate of frequency and danger. Shielding is limited because the threat is not a rock you can deflect. The atmosphere is the target, and the atmosphere is also the conduit. You cannot put a roof over a planet, and you cannot easily thicken an atmosphere on demand. The very thing that normally protects life becomes the medium that converts radiation into long-lived chemical change. Magnetospheres help only at the margins. Earth's magnetic field deflects charged particles, yet it cannot stop gamma rays and hard X-rays. A strong magnetosphere can reduce some particle precipitation, and may influence how secondary electrons move, but it cannot prevent ionization initiated by photons. In plain terms, a magnetic field is a shield against bullets with charge, not against bullets made of light. Thicker atmospheres can absorb more energy higher up, but that does not guarantee safety. It can shift chemistry into different layers and still destroy ozone. A dense atmosphere can protect the ground from secondaries more effectively, yet it also provides more targets for ionization and more nitrogen and oxygen to convert into reactive forms. Protection is therefore conditional, and the conditions depend on composition, circulation, and photochemistry. Oceans provide local refuge, not planetary immunity. Surface ecosystems still suffer, and food webs still depend on sunlight-driven productivity. Water attenuates ultraviolet, and deeper layers can become temporary sanctuaries, yet most marine life depends on what happens near the surface. If surface productivity declines, the deep ocean eventually feels it through reduced organic flux. Now address the hardest part. How much warning would we get if the next giant flare were close enough to matter? The answer is uncomfortable because it is physics. The radiation arrives at light speed, so warning is limited to whatever the source does before the flare. There is no incoming shockwave to detect early, and no gradual brightening that must precede the event. If the Magnetar is quiet, the first sign may be the flare itself, an arrival that is by definition simultaneous with detection. Magnetars sometimes show increased bursting before major events. They can enter active phases with storms, torque changes, and spectral hardening. In X-ray monitoring, this can look like a rising crackle of short bursts, changes in pulse profiles, or shifts in spin-down rate as the magnetosphere reconfigures. These are clues that stress is building, like small quakes before a larger rupture. Those precursors are not reliable alarms. Some active phases do not culminate in a giant flare, and some giant flares may have subtle let-up. The magnetar's crust and magnetic field interact in ways we do not fully predict, and the system can release energy in many smaller events instead of one large one. A warning that cries wolf too often becomes operationally useless, especially for high-cost responses. Even if a precursor is detected, the lead time may be hours to days. That is not enough to protect a biosphere, and it is barely enough for technology. You can shelter people from acute radiation with mass and distance, yet you cannot shelter an atmosphere from ionization. The best you can do is reduce secondary harms, protect satellites, manage aviation exposure, and brace critical infrastructure. We could power down satellites and reroute flights if we believe the warning. The problem is that belief requires prediction, and prediction remains weak. Operators need probabilities, not possibilities, because shutting down systems has consequences of its own. The uncomfortable question becomes practical. How often would we accept disruption on a false alarm to avoid one rare, severe event? Detectability is also biased by dust and monitoring gaps. A magnetar behind the galactic plane can be quiet in our data until it is suddenly not. Interstellar gas and dust absorb soft X-rays, and crowded star fields complicate identification, so some objects remain hidden unless they flare. Our sky surveys are better than they were, yet they are not omniscient, and the galaxy is large. The event itself would be unmistakable in instruments. The spike would saturate detectors, and the ionosphere would respond globally within seconds. gamma-ray satellites would register a sudden, overwhelming signal, while ground-based monitors would see ionospheric disturbances ripple through radio bands. It would be a moment when multiple disciplines – astronomy, atmospheric science, electrical engineering – converge on the same timestamp. For life, the danger is not the flash itself. The danger is the months of altered sunlight and the years of ecological recovery that may not complete. A flare can be over in minutes, yet the ozone deficit can persist through seasons, exposing each new generation to a different sky. The planet's memory of the event is written in chemistry, not in craters. Compare this to known extinction stresses carefully. Ozone loss and UV stress resemble parts of volcanic and impact aftermath, yet the trigger is different. Impacts loft dust and sulfate aerosols. Volcanoes can inject sulfur and ash, and both can cool the surface by blocking sunlight. A Magnetar flare does not need to dim the sun. It can make the sun more dangerous by altering what reaches the ground. A Magnetar flare does not inject soot or aerosols. It changes atmospheric chemistry directly, and that can stress ecosystems without cooling the planet. That distinction matters because it changes which organisms are hit first and which refuges remain available. If temperatures stay broadly similar while UV rises, the stress pattern is skewed towards surface exposure and photobiology. That difference cuts both ways. It may reduce some pathways of collapse, yet it concentrates damage into biology's dependence on stable UV filtering. Some ecosystems might avoid the freezing and famine associated with impact winters, yet they would face chronic radiation stress in the photic zone. The question becomes unsettling. How much of Earth's biosphere depends on the ozone layer being not just present, but stable? Uncertainty remains, and it must be stated without deflating the tension. We do not know the beaming pattern, the true flare energy distribution, or the spectrum. We also do not know how often magnetars produce the most extreme events, because our observational window is short and our instruments have limits. In rare event science, the tails of the distribution matter most, and the tails are where data are thinnest. We also do not know the exact biological thresholds for global sterilization. We can model ozone depletion and UV increase, yet ecosystems are complex. Species differ in UV tolerance, repair capacity, and behavior, and the web of interactions can amplify small changes. A biosphere is not a single organism, it is a network, and networks can fail gradually or suddenly. Still, the mechanism is not speculative. Ionization makes NOx. NOx destroys ozone catalytically, and UVB rises across the surface. These are established chemical pathways, tested in laboratories, and observed in Earth's atmosphere under other perturbations. The Magnetar is the exotic trigger, but the atmospheric response uses familiar rules. Now place the risk in context. Giant flares are rare, with only a few observed clearly in the modern era. The famous events 1979, 1998, and 2004 entered the record because they were bright enough to be noticed across the solar system. They also arrived during an era when we had satellites watching, which is a reminder that earlier events could have passed unrecorded. The 1979 flare, detected from SGR 0526-66, startled a young field that was still sorting cosmic gamma-ray transients. The 1998 event from SGR 1900+14 reinforced the pattern, showing that magnetars can repeat on human timescales. Then 2004 arrived with SGR 1806-20, so bright that it briefly reshaped the conversation about what nearby danger could mean. For a moment, researchers asked whether some short gamma-ray bursts might be misidentified Magnetar flares seen from other galaxies. Rarity is not reassurance when consequences are global. A low rate multiplied by geological time still yields non-zero odds. Civilizations think in decades, but planets endure for billions of years, and low probability events become inevitable when the clock is long enough. The unsettling arithmetic is that rare is not the same as never. The Milky Way likely hosts more magnetars than the few dozen confirmed. Many are hidden, inactive, or simply unmonitored in the right bands. Magnetars are thought to be young neutron stars, born from massive star supernovae, and they may remain active for only a fraction of cosmic time. That means the galaxy's magnetar population is dynamic. Objects appear, flare, quiet down, and fade. The probability of one within dangerous range is uncertain. It depends on the true magnetar population, their lifetimes, and the distribution near the Sun. It also depends on where massive stars formed in the recent past, because magnetars do not wander far before their activity declines. Our neighbourhood is not the galactic centre, yet it is not empty, and history matters. The nearest known magnetar is far beyond the worst-case threshold, yet catalogues are incomplete. The absence of evidence is not evidence of absence. We have found many magnetars through their outbursts, which means quiet ones are harder to tag, and obscured ones can hide in the plane. The map we have is a draft, and the margins are where surprises live. This chapter is the climax because it answers the hook with mechanisms. A magnetar could kill a planet without touching it by turning air into an amplifier. The planet is not struck by a physical object, yet it is struck by a change in its own protective chemistry. The atmosphere, which usually softens space into sky, becomes the pathway by which space reaches down. Now the narrative turns from helplessness to agency. If distance and beaming set the hazard, then mapping magnetars becomes a form of planetary situational awareness. Knowledge does not stop a flare, yet it can define risk, refine models, and guide infrastructure planning. It can also tell us whether we live in a quiet neighbourhood or merely an unmeasured one. The deeper question is almost philosophical. How much safety comes from physics, and how much comes from knowing where the physics is hiding? We transition from threat to surveillance. The next chapter follows how we search for magnetars, measure their activity, and draw a safety margin across the galaxy. The hook was never impact or fire. It was light crossing deep space and chemistry failing in silence. In our minds, disaster arrives with sound and debris, with a crater you can point to on a map. A magnetar's threat is stranger. Photons arrive first, and the atmosphere does the rest. The danger is not heat on the ground, but ionization in the sky, and that difference changes everything. We asked what makes magnetars uniquely lethal, and how close is too close for Earth. The answer is not a single number, but a margin shaped by distance, spectrum, and beam geometry. It is a problem of exposure and alignment, where the same flare can be harmless to most targets and catastrophic to one. A giant flare is a brief spike that can do the most harm, followed by a tail that explains the engine. The spike is the part that couples fast to air, and it is also the part we measure worst. In those first fractions of a second, detectors saturate, and physics outruns our instruments. The tail, by contrast, is a slower pulse train that often tracks the star's rotation. It is like hearing the ringing of a bell after the initial strike, and it tells us the magnetosphere is reorganizing. That long decay is where we glimpse trapped plasma, twisted field lines, and energy leaking away in a controlled collapse. So the final question becomes practical. How many magnetars are out there? Where are they hiding? And how early can we recognize one? If the hazard is rare but severe, then the difference between fear and understanding is an inventory. Start with where they live. Most known magnetars cluster near the galactic plane, where massive stars are born and die quickly. On a wide Milky Way map, the plane is a bright band of structure, spiral arms, molecular clouds, and star-forming knots stitched together by dust lanes. They track star-forming regions because their progenitors are short-lived, and their youth keeps them near their birthplaces. A massive star can burn through its fuel in a few million years, which is a blink on galactic timescales. When it collapses, the newborn neutron star has not had time to drift far from the nursery. They also appear near supernova remnants, where expanding shells mark the recent collapse. In radio and X-rays, those remnants look like ghostly bubbles, filaments, and arcs. Shock fronts sweeping up interstellar gas. When a magnetar sits near the centre, the geometry feels like a signature left by the explosion. Those associations are imperfect, because remnants fade and magnetars can receive natal kicks. A magnetar can drift away from its remnant, or the remnant can be too faint to identify. The kick can be hundreds of kilometers per second, and over tens of thousands of years that becomes a meaningful separation. The plane is also where the galaxy hides its own inventory. Dust and gas absorb optical light and soften X-rays, turning whole sight lines into blind corridors. Even in X-rays, photoelectric absorption rises steeply at lower energies, so a source can vanish simply because its photons are too soft. This is why catalogues feel confident and incomplete at the same time. We find magnetars when they burst, and we miss them when they behave. The quiet ones are not necessarily rare, they are simply harder to notice against a crowded, obscured background. The nearest known magnetar is often summarized as about 9,000 light-years away. That sounds like a clean safety buffer against the rough 1,000 light-year danger scale. But the comfort of that number depends on what known really means. Closest known is not closest existing. It is a statement about detection limits, survey coverage, and how magnetars announce themselves. It also reflects how uneven our attention has been, because the galactic plane is wide and instruments have finite time. Distance itself is not a single measurement. It is inferred from absorption, associations, and sometimes kinematics, each with systematic uncertainty. We compare X-ray spectra to models of interstellar gas. We look for nearby clusters, and we sometimes use proper motion to estimate how far a source must be. A few thousand light-years of error is plausible in the plane, where extinction is patchy and line-of-sight structure is crowded. Two clouds at different distances can overlap in the same direction, and the spectrum only tells you the sum. Energy estimates scale with distance squared, so risk estimates inherit that uncertainty. Selection effects do the rest. Soft X-ray absorption hides cooler or quieter magnetars, and burst-triggered discovery favours the loudest phases. If a magnetar spends most of its life in a dim state, we are biased toward catching it only when it becomes dramatic. Even timing searches have bias. A weak pulse signal can be lost in background, and irregular torque noise can smear the periodicity. Magnetars are notorious for timing noise, where the spin-down rate wanders as the magnetosphere changes. So the real safety margin is statistical. It is the probability that no active magnetar sits within a threatening distance, not a guarantee. That probability improves as catalogues improve, yet it never becomes absolute. Now we transition from where they are to how we find them. The method is the message, because each method defines what we can miss. Every detection technique is a filter, and every filter has a blind spot. The first net is X-ray timing. Magnetars reveal themselves as slow rotators with large spin down, implying strong dipole fields. Their periods cluster around a few seconds, and their period derivatives can be enormous compared to ordinary pulsars. We measure period and period derivative, then infer a characteristic field strength, while remembering that multipolar fields can dominate locally. The usual estimate assumes magnetic dipole breaking in vacuum, which is a simplification, but it gives a useful scale. It tells us that the large-scale field can be 1,000 times stronger than typical pulsar fields. Timing also catches glitches and anti-glitches, which hint at superfluid interiors and magnetospheric torque changes. A glitch is a sudden spin-up, often interpreted as angular momentum transfer from a superfluid component. An anti-glitch, rarer and more puzzling, suggests that magnetospheric currents can abruptly increase braking. Persistent X-ray emission is another handle. Magnetars shine in X-rays beyond what rotation can power, implying magnetic heating and twisted magnetospheres. The surface can be heated by field decay, and the magnetosphere can scatter photons, reshaping the spectrum into hard tails. In visuals, persistent emission is not a flare, but a steady, eerie glow on false colour maps. It is the star's magnetic budget leaking away, year after year, as the crust and magnetosphere adjust. In plain terms, the magnetar is spending its field like a battery, and the X-rays are the receipt. Burst monitors form the second net. All-sky gamma and hard X-ray instruments catch short bursts and rare giant flares, even when the source is otherwise invisible. These monitors watch continuously, because magnetar bursts do not schedule themselves. This is how many magnetars enter catalogues, through sudden spikes that saturate detectors and force reconstruction. It is effective, but it is reactive, and it gives no warning before the first pulse. When the spike is too bright, we infer its true shape from scattered counts, dead time, and even reflections off spacecraft. The spike spectrum matters because it decides how the atmosphere responds. Hard photons penetrate deeper and ionize more efficiently, while softer photons are absorbed higher up. That is why how close is too close depends on energy distribution, not just total energy. Radio follow-up is the third net, and it is newer than the magnetar concept itself. Some magnetars turn on as radio pulsars after outbursts, with unusual spectra and variability. Their radio emission can be bright, then vanish, then return, like a lighthouse whose beam is sometimes blocked by its own weather. Radio timing can localize precisely and measure dispersion, which constrains distance through electron content models. Dispersion is a delay across frequency, caused by free electrons along the path, and it is one of astronomy's most practical yardsticks. Yet electron models have structure, so dispersion distances remain approximate. Sometimes the radio pulse profile itself changes as the magnetosphere relaxes. A pulse can broaden, split, or drift in phase, and those changes are clues to current systems above the surface. In a magnetar, the magnetosphere is not a passive vacuum, it is an active circuit. Polarization adds a deeper layer. Strong magnetic fields imprint polarization signatures through propagation effects, including QED vacuum birefringence in the right regimes. In that regime, empty space behaves like a crystal, and light's polarization can rotate as it travels. X-ray polarimetry can test whether magnetar magnetospheres are twisted, and whether surface emission is strongly beamed. These measurements help turn field strength from an inference into a geometry. They also help separate surface hotspots from magnetospheric scattering, which can otherwise mimic each other. Localization matters because environment matters. If a magnetar sits in a star-forming complex, it supports a massive star origin pathway. The surrounding gas, clusters, and metallicity become part of the story, not just scenery. If it sits in an older region, or shows evidence of fallback burial and re-emergence, it complicates the birth story. Fallback can bury magnetic flux under accreted material, delaying the appearance of a strong external field. If the field later diffuses back out, the magnetar may look young magnetically but old dynamically. The origin question remains open because multiple channels can produce similar present-day behavior. The same observed spin and luminosity might arise from different internal configurations, and nature rarely offers a single pathway. In a sense, magnetars are a class defined by symptoms, not by a single confirmed cause. Future nets expand the search volume and reduce the blind spots. More sensitive X-ray monitors increase duty cycle, so quiet phases become measurable instead of invisible. That matters because a quiet magnetar can still be nearby, and proximity is what turns rarity into risk. Wide-field hard X-ray and gamma missions improve dynamic range, so the next giant flare is less likely to erase its own peak. Better time resolution helps separate spike physics from instrument limits. When you can resolve milliseconds cleanly, you can test whether the spike is one event or a chain of micro-reconnections. Ground arrays add a different kind of net. Radio interferometers can catch transient counterparts and map magnetar neighborhoods with high precision. With long baselines, the sky becomes a ruler, and positions shrink from arc minutes to milliarc seconds. Fast transient pipelines can trigger multi-wavelength follow-up in minutes, which matters because magnetar outbursts evolve on hours to weeks. The goal is not only discovery, but characterization while the system is changing. Watching the spectrum soften, the pulse shape drift, and the torque wander is how we learn what the engine is doing. There is also the gravitational wave era, where multi-messenger context changes what magnetars mean. Some neutron star mergers may leave behind a long-lived magnetar remnant, at least temporarily. If it survives collapse, even briefly, it can dump rotational energy into its surroundings at an astonishing rate. That remnant would inject energy into a ejector and change kilonova-like curves, linking magnetar physics to heavy element production. It would also connect magnetic topology to the life cycle of matter in galaxies. In visuals, the connection is stark, an expanding cloud of debris glowing in infrared, powered from within by a compact unseen rotor. Now we transition from Milky Way bookkeeping to cosmology. Magnetars are not only local hazards, they are engines that may light up the distant universe. Once you can recognize their signatures, you start seeing them echoed across billions of light years. Fast radio bursts sharpen this link. At least some repeating FRBs resemble magnetar activity, scaled up and seen across intergalactic space. Their durations are milliseconds, but their implied brightness temperatures are extreme, demanding coherent emission. The galactic magnetar SGR 1935+2-154 produced an FRB-like radio burst, tying the class to a known magnetar mechanism. That does not solve all FRBs, but it proves the channel exists. It also tells us that magnetars can produce radio flashes that would look cosmological if they happened in another galaxy. If magnetars power some repeating FRBs, then magnetar activity is not rare in cosmic terms. It implies that young, highly magnetized neutron stars are common outcomes of massive star death across galaxies. It also suggests that the universe is full of brief, sharp radio cries we only notice when our instruments happen to be listening. It also implies that magnetars can release energy in multiple bands, with beaming and selection effects shaping what we call an FRB. The same object can look like a radio transient at one distance and a gamma transient at another. Classification becomes a function of sensitivity, not just physics. This matters for rates. If extragalactic magnetar flares masquerade as short GRBs when tails are undetectable, then giant flare frequency may be undercounted. The spike alone can resemble a short gamma-ray burst, especially when the softer, longer tail falls below threshold. Rate estimates then feed back into Earth risk. A higher true rate increases the chance of a nearby event over geological time, even if the yearly probability stays small. Over tens of millions of years, small can still become eventually, and that is the scale where biospheres keep records. Yet the risk is still governed by geometry. Beaming can make the dangerous spike narrow, which reduces the fraction of targets hit while increasing the dose for those aligned. A narrow beam is safer in aggregate, but harsher for the unlucky line of sight. We do not know the beaming geometry well, especially for the initial spike. We also do not know how often magnetars reach the extreme tail of the flare distribution. Those two uncertainties multiply, which is why hazard estimates remain cautious. These unknowns are not cosmetic. They set the true kill radius, because a hard, beamed spike changes everything. If the spike is both harder and narrower than we assume, then safe and unsafe become more about orientation than distance. Open questions begin inside the star. The crust is only a skin, and the core may be superfluid and superconducting, changing how magnetic fields evolve. At nuclear densities, matter behaves in ways we can only approximate with theory and indirect constraints. If the core hosts superconducting flux tubes, field motion may be pinned and then released, producing stress cycles. In that picture, magnetic flux is not free to slide smoothly. It is trapped in quantized structures. When those structures unpin, the release can be abrupt, like tectonic plates that suddenly slip. If the interior is more complex, the field may rearrange in ways our models still approximate. Composition gradients, exotic phases, and temperature evolution can all matter, and each adds a new timescale. The magnetar's external behavior may be the surface trace of a deeper, slower negotiation. Magnetic topology is another gap. The dipole inferred from spin-down may be only the large-scale component, while multipoles dominate near the surface. A strong quadrupole or octupole can concentrate stress and heat into smaller regions. Multipoles change where currents flow, where hotspots form, and how radiation is beamed. They also change how reconnection proceeds during a flare. In a twisted field, the magnetosphere can store energy in currents, and the release can be sudden when stability is lost. Trigger physics remains contested. Some models emphasize crustal yielding that shifts foot points, others emphasize magnetospheric instabilities that snap without a major fracture. The truth may be hybrid, where a small crustal motion nudges an already stressed magnetosphere past its threshold. Alphen waves likely couple interior motion to the magnetosphere, but the exact threshold for runaway reconnection is uncertain. The spike happens faster than most internal processes, so the trigger must be efficient. That efficiency is part of what makes magnetars feel like traps. Energy stored slowly, released almost instantly. Giant flare rates remain the hardest statistic. We have a handful of clear events, and a short observational baseline compared to magnetar lifetimes. The famous flares of 1979, 1998, and 2004 are landmarks, but 3 landmarks do not define a continent. We can model populations and infer rates, but the confidence intervals are wide. Rare event tails dominate hazard, and tails are where data are thinnest. It is an uncomfortable truth of risk science that the most important events are often the least sampled. So what does finding magnetars before they find us actually mean? It means building catalogues that are less biased, and monitoring that is less episodic. It means turning discovery from an accident into a system. It means mapping the plane in hard X-rays where dust matters less, and using infrared and radio to identify obscured remnants and clusters. Infrared surveys can reveal young stellar groups behind dust, and radio can trace supernova shells long after optical light fades. Together they give context for where magnetars should be, even before one flares. It means treating the galaxy as an environment with hazards, not only as a backdrop. We already map near-Earth asteroids because proximity matters, and magnetars are the same logic at a different scale. The difference is that magnetars do not approach. Their influence arrives at light speed. It also means treating Earth as part of the detector network. Ionospheric monitoring, satellite health telemetry, and gamma-ray sentinels together provide rapid confirmation and reconstruction. When the upper atmosphere suddenly changes conductivity, it is a global instrument responding to a cosmic input. In a reconstruction, you might see a spike in high energy counts, then a ripple through the ionosphere, then subtle anomalies in radio propagation. Each is a different window on the same event, and each helps constrain the spectrum. Even when a detector saturates, the planet's response can preserve the story. But warning remains limited by light speed. The best-case scenario is recognizing a magnetar entering an active phase, then assigning probabilities rather than certainties. We can say the system is restless, we can quantify its recent bursts, and we can watch for escalation. But we cannot outrun photons. That is the sober resolution of the central question. Magnetars are uniquely lethal because they can weaponize light into a chemical cascade, and distance is the only real shield. The atmosphere is both our protector and our vulnerability, because it absorbs the energy and then transforms. The rough 1,000 light-year line is not a wall, it is a scale. Spectrum, duration, and beaming can move it, and our uncertainty moves with them. A softer flare might be mostly harmless at that distance, while a harder, tighter beam could matter farther out. Our current catalogue suggests no known magnetar sits inside that scale, and that is meaningful. Yet incompleteness means we should treat the margin as provisional, not permanent. The galaxy is large, the plane is crowded, and quiet objects do not volunteer their addresses. The point is not to inflate dread. The point is to replace vague fear with measured context, because context is how the darkness becomes navigable. When you can name the uncertainties, you can reduce them, and that is the difference between myth and science. Magnetars are cosmic horror made real, but they are also laboratories. They let us test QED and strong fields, probe superdense matter, and connect stellar death to galactic ecology. They are places where theory meets extremes, and where nature's most intense magnets force our equations to behave. They also remind us what astronomy is for. We look outward to understand what can reach us and what cannot. We measure the sky not to invite fear, but to set boundaries around it. Now we return to the hook, because the ending is the same mechanism that began the story. No impact, no explosion, no warning siren in the sky. Just a brief, hard flash that arrives already finished, and a planet that must respond in real time. Just light. Our defense is distance, knowledge, and the nets we keep watching the sky with. Across this journey we met a stellar corpse only 20 kilometers wide, yet able to bully a planet from light years away. Its power is not gravity or impact, but magnetic energy stored like a wound-up spring, twisting the magnetosphere, stressing the crust, and waiting. When that stress finally slips, through starquakes, Alphen waves, and reconnection, the result is a giant flare with a signature we now recognize, a blinding millisecond spike, and a pulsing tail that cools inside a trapped fireball. We followed the physics all the way down to the Schwinger limit, where fields polarize empty space, atoms deform, and hard light becomes a tool that can ionize air. Then we trace that light through Earth's sky, where broken nitrogen and oxygen assemble into NOx, ozone collapses faster than it can heal, and the real catastrophe arrives days later as ultraviolet, ecology, and climate feedbacks begin to unravel. Even from 50,000 light-years away, SGR 1806-20 left fingerprints in our ionosphere and in saturated detectors, reminding us that the most important part of a flare can be the part instruments cannot fully capture. And we ended with the uncomfortable accounting, because distance, spectrum, and beaming set the true kill scale, while dust, absorption, timing noise, and selection bias keep our catalogues incomplete. Magnetars are uniquely lethal because they weaponize magnetism into radiation, converting interior stress into a galaxy-spanning pulse that can rewrite chemistry, not merely scorch surfaces. Yet every chapter also showed the counterweight to dread, because the same spike and tail pattern, torque noise, glitches, polarization, and burst statistics give us handles to measure the monster we cannot touch. Even the birth question remains open. Flux-frozen inheritance, millisecond dynamos, mergers or buried fields. Yet each origin leaves clues in spin, environments, supernova remnants, and population counts that future surveys can test. So the story is not just cosmic horror, it is a map taking shape, where uncertainty shrinks as our instruments widen their net and our models learn to speak the atmosphere's language. So, would we notice if one ignited within 1,000 light years before electronics and biology went dark under an invisible shockwave? The honest answer is that too close is not a single number. Beaming, hardness and duration could move the line inward or outward, and we might only recognise the danger after the first photons have already done their work. But the deeper answer is also clearer now, because magnetars do not need to touch Earth at all, they only need to point. A nearby giant flare would announce itself as a split-second detector-breaking spike, followed by a rotating after-echo in hard X-rays, while the planet's real emergency would unfold quietly in the chemistry above us. The existential threat is not fire, it is conversion, a temporary flash that buys years of altered sunlight and weakened shielding, and our safety margin is therefore a probability, not a promise, bounded by how many magnetars we have missed, how often giant flares truly happen, and how narrowly the worst part of the beam is aimed. In the end, magnetars are terrifying for the same reason they are beautiful, because they prove the universe can turn pure physics into consequence without warning. A dead star can make light behave like a weapon, and make air behave like fuel, and do it from the far side of the galaxy. But there is another lesson hiding inside the fear, because every time we reconstruct a saturated spike, measure a polarized X-ray, or catch a timing glitch, we trade helplessness for geometry and superstition for constraints. The cosmos is not kinder when we understand it, yet it becomes less mysterious in the only way that matters. Our ignorance stops being the largest part of the risk. Somewhere in the Milky Way, magnetic fields are still winding and cracking, still rehearsing their silent scream, and the difference between nightmare and knowledge is whether we are listening. If magnetars are cosmic horror made real, then astronomy is how we keep the lights on, not by controlling them, but by refusing to look away. Support the missions and surveys that watch the high-energy sky. Wide-field monitors, X-ray polarimeters, radio timing arrays, because the best defense against invisible physics is a bigger, smarter net.